let me share my slides. Okay, ready?
Mm-hmm.
Yeah, great. Okay, yeah, so very excited to be here. Thanks for the invitation. So I'm going to talk about sort of what maybe I'd consider somewhat a crisis in adversarial machine learning. Maybe it's not quite, maybe it's a little bit overblown, but I like this title for the talk, so I'm going to go with it. Okay, so what am I going to talk about? I'm going to talk about progress we have or maybe haven't made in getting where we wanted when we started out in this field. So why do we study adversarial machine learning when we decide to do this? I mean, sometimes we just do it for fun, but we also like to have some concrete objectives of what we might like to achieve. And so people have a couple of things they might want to do with this. So generally speaking, some people say like they might want to improve like general purpose robustness, like you're studying adversarial robustness as a lens to understand general purpose robustness, and hopefully by improving things in the worst case, you can also make things better on average. This is one kind of argument people make, and in principle, I think it's true that improving adversarial robustness should improve robustness in general, but it hasn't worked out that way so far very much. And so actually, I'm not going to talk about this all that much because I think Ludwig actually might sort of touch on this at his talk in a couple hours. So I'm going to sort of just skip this for the most part, and instead talk about the other reason that people tend to think about adversarial robustness, which is that we might want to study this because we might want to improve the robustness against worst case attacks. Like you might be worried against someone who's trying to fool your model, and you just want to have this complete security motivation. You're not considering any potential other benefits that these models might have. You just want to try and make them more secure. And here, things have not gone amazingly well. So for example, let's go back in time to like the year 2014, and suppose that someone tells you they have an algorithm to generate like synthetic images. What they'll be showing you are images that look like this. This is sort of from the GAN paper from Goodfellow. And they kind of look like faces if you squint a little bit. They're like really low resolution black and white images that more or less resemble something like a human face. But they're pretty bad. Not many years later, 3 years later, years 2017, and someone tells you they have an algorithm to generate synthetic images, they'll be able to show you images that look like this. 2 of these are real people and 2 of them are fake. I forget which are which by now. It's been long enough that like they look all the same to me. They're very, very good. This is what 3 years of progress showed in regular machine learning. And then if you ask for the same thing again today, right? Like you said, like you have an algorithm to generate synthetic images. Now you might see like an image that looks like this, which is like, completely amazing and just unthinkable just a few years ago. But, you can ask for a particular image of a corgi riding a bike in Times Square, wearing sunglasses and a beach hat, and it will like do all of the things for you. Okay, so that's kind of amazing. We sort of in 8 years went from this half recognizable image of a face to like these photorealistic, just like arbitrary images you can come up with, and it will just create it whatever you want. Okay, in contrast, the year 2013, and someone tells you they have discovered a flaw in the robustness of neural networks. They'll show you that this image here is incorrectly classified by a neural network. I think this one was like a 4 or something. This one is from Battista Biggio's paper on the vision attack at test time. Okay, this is a problem, but like, that was 9 years ago now. And so someone tells you, it's today, someone tells you they discovered a flaw in the robustness of neural networks. And you ask like, what's the best image that you could use before you had to get a misclassification? And the answer is something like this, where this image is misclassified as an 8 by a state-of-the-art MNIST trained model. And so like, we're in this world where somehow in 8 years, we can go from something that looks very, very bad to something that looks very good in one field. In a similar field in machine learning, we have 9 years of progress, and it looks like we've made almost no progress. And of course, I'm showing MNIST here because if I were to show you ImageNet results, you just wouldn't be able to see a difference. Like the sort of the robustness is essentially, perceptually completely invisible on ImageNet. At least on MNIST, you can see that there's like some perturbation that's been added here. And so this really begs the question, like, what have we been working on for the last 9 years if we can't even do handwritten digit classification correctly? This adversarial example here is an adversarial example on an adversarially trained model, one of the state-of-the-art MNIST models that's adversarial. Okay, so this is like a little sad, right? I don't think that we've made no progress, but I think we've made much less progress than we might have hoped to make a couple of years ago. So you might say, like, why has this happened? And one reason why, which is true, is like defenses are really, really hard. Like it's very hard to construct defense because you have to be robust to essentially everything. The attacker gets to sit down afterwards and come up with the most effective attack they can, and you have to hope that it works there. Okay, but that can't be the only reason why. So let's go back a couple decades to the field of symmetric key cryptography. This is sort of a field that at one point in time had exactly this kind of problem, where every sort of 6 months or so, you'd get another paper that was like a break on some symmetric key cryptographic system. All of these papers I took are like just the papers from my advisor that he wrote in a period of like a couple of times when I was at Berkeley. And so very much this was a problem at the time, from 1995, 1997, 1998, like every couple of years, everything would be awful and you just get a completely new break on a system. In contrast, maybe less than 6 years after that, we have AES, which is essentially perfect against all attacks. Like the best cryptanalysis on AES has been unchanged for the last decade, and we've basically solved everything. So it can't just be that like defenses are hard, because like we have this existence proof where we went from like in less than 6 years, lots of papers coming out just breaking these best systems, to all of a sudden, no breaks. We've essentially figured it out. So it's not just the fact that that defenses are hard. It's a little bit worse because like for some reason, we still can't stop publishing defenses at top venues that like are trivially broken by undergrads. And I'm not being like this is actually the case, right? Like earlier this year at iClear, I wrote a paper with 4 Berkeley undergrads who are brilliant, but like they only have so much experience in this field, and we could break several state-of-the-art defenses that were published at top machine learning and security conferences. And so this sort of really begs the question, like, what's going on, that like we've been at this for so long and it's still the case that we just, try something slightly new and then you end up breaking some defenses that people thought were secure. Okay. And to be clear, I want to be not that we've made zero progress, right? Like we've made a lot of progress. For example, we were sort of really good at knowing how to evaluate defenses correctly if we try really hard. There have been some nice talks just before this one at the conference. Maybe I'll call out Roland's that was done when he was doing an internship with us, which I think is a very nice result for like showing how to do these evaluations more correctly. But there were a couple others that were just also right after Roland's that talked about this as well, which are also very nice. So, we've gotten very good at like knowing how to do these evaluations, and that's at least some progress. But maybe like the result I'm like most surprised by is maybe like these certified robustness numbers. In 2017, I was giving a talk on like the first talk that I gave on robustness, and I said that like at the time, the line I said is that you could try and prove robustness, but that's basically impossible and not going to work. So let's do attacks. Of course, 5 years on, and actually we can prove completely non-trivial things about ImageNet models. This is from the randomized smoothing paper, and we can actually do like actual certification of robustness on ImageNet, which is really, really quite impressive. Actually, it's like a slight teaser for like sometime maybe tomorrow, or I guess tomorrow's a holiday on arXiv, so it won't be released tomorrow, but maybe the day after, that we'll put up a paper that actually improves these results by a little bit. It's sort of actually another maybe in one way kind of a negative result. It turns out that if you just use sort of off-the-shelf diffusion models, you can just like beat every adversarially trained like sort of fancy model for image classification robustly, which is again, maybe a little bit interesting that in order to get the best robustness you could hope for, instead of training models ourselves, like in the security adversarial machine learning community, if we just take like one off-the-shelf diffusion model, like we can sort of beat all of those. So that's maybe in some sense a little bit of a negative result again, but regardless, the techniques that are sort of necessary, the pixel DP into randomized smoothing into denoise smoothing into these things sort of are quite impressive. So like, to be clear, like we have made some progress. The problem is that the amount of progress we've made maybe is somewhat less than we might want. So for example, these two images have an L2 radius of 4 separating them. And they look completely indistinguishable to us as humans, but despite that fact, you know, like this is the kind of certification we can do. Like we can kind of verify with like 10% probability that we can get the image on the right correct. And like, you know, in practice, what we really want is we want like, much more noise. You know, you might want this image that's over here on the right that has a 75 norm perturbation. And more than that, you know, you not only want to be like, up there on the left here, you want to be like way over here. So we are, several orders of magnitude away from being where we really need to be to have robust models. So in some sense, this is quite bad. Because you can have this image here that's like you'd like to be able to become classified correctly, but it's also even worse because this image also has an L2 distortion of 75, but like obviously we probably wouldn't want this one to become classified. Like this is probably too much of a perturbation in some sense, while this one is still too little. And so like even once we get to these large norms, the distance metrics we have are going to break down, and so we're going to run into even more problems there. So, okay, this is me being quite negative. Let's try and change things around just a little bit and say, instead of trying to think about the robustness against worst case attacks, which has been very, very challenging to say the least, maybe one thing we can still make progress on that like we can show like as an actual result of what we've been doing is to try and improve the robustness against practical attacks. Because it's fine for us as the community to spend a lot of time, in the weeds trying to solve really hard technical problems. But I think every once in a while, it's important to sort of come back up and see if we've learned anything, if we can use what we've learned in order to make the world better. And the reason why I think it's especially important in security is that when you analyze the security of something, it really only matters if the thing you're securing is ever used. You can analyze the security of lots of things no one actually uses, and then the security of them is not really important because no one uses them. And so I think it would be nice if in this field we tried to spend a little bit of time looking at the robustness against some kind of practical attacks. Okay. And people do try and say they do this, right? Like there are papers that are written on like adversarial attacks on medical machine learning. And they try and sell this as a practical result. And I disagree with that a little bit. And to be clear, I'm not just sort of blaming this one paper. There are like a lot of papers that try and do this that all say like, let's think about adversarial examples for like COVID-19 diagnoses or something. And it's not clear to me that any of these are practical attacks, in the sense that no one, when confronted with a machine learning model and that does a medical diagnosis, and if you ask them like, how are you going to break this? Are they going to generate adversarial examples, right? Like if you can perturb the images that go into the machine learning model, you could just replace them with something completely different. You can, just make the model output no or yes or however you want. Like the threat model here, like just doesn't make sense. Like there's no reasonable threat model for an adversary who like when forced to attack a medical diagnosis system is going to use adversarial examples. Like I agree that the attacks are nice and they're clever research ideas, but this is not a practical thing. I would like people to focus on attacks that someone would actually want to mount. And so for this, I think, thinking about threat models here really is quite important. And so my hope is that the field will be able to move somewhat in the direction of coming up with attacks with threat models that that sort of are well motivated by an adversary who might actually exist out there in the world. So what do I mean by this? One of the cases I can think of that would make a lot of sense would be abuse detection. So you have these tools out there that are currently deployed everywhere that try and detect abuse. This is everything from messages on Discord, from like trying to prevent people from saying abusive content. Wikipedia does this so that whenever you try and edit an article on Wikipedia, it will try and see if what you're doing is just some kind of vandalism, and it will revert automatically if it's just straight vandalism. And then all the search engines have these filter for explicit content, which are again similar kinds of models that trying to filter out and show people a safe part of the internet. And this is one area where I think it would be really important to actually understand how secure these systems are. Like, these are real systems that are in use, protecting people today. And there is an adversary here. But for some reason, as far as I'm aware, I haven't seen any actual attacks on these live systems. And we can, go in our basements and sort of try and attack ImageNet models in isolation. And we've gotten really good at that. But the real question I have is how much of that transfers to attacking these systems that appear in production? Because there are a number of differences, right? These aren't systems we have gradient access for. These aren't systems that we can send an arbitrary number of queries to. At some point, they'll detect that something's going on and it sort of becomes suspicious. And we don't necessarily completely understand exactly what these models are doing. And so I think we could learn a lot by trying to attack some of these systems that are out there in order to see what it would actually mean to break a real system that's currently deployed. So, for example, this doesn't mean that we have to do, a straight, what we might think of as an adversarial example attack, right? Like, we don't have to minimum LP norm perturbations in order to fool these systems. To see this, I think there was this article last year that was talking about some abuse that was going on for OnlyFans, where people were trying to detect, abuse to keep people safe, right? This makes lots of sense. You want to keep people safe. And, in the article, the company said the racial slur was not detected because by the site's moderation system because it was pluralized. And this is a little bit bad from the defense side, but it also means that the attacks that we have are so much more powerful than this. It really should be quite trivial to evade many of these systems. And I would like to see it happen in the academic literature so that we're not learning about these attacks because there's some news article in the BBC. It would be awfully nice if our research community that is pretty good at trying to evaluate the robustness of systems had evaluated the robustness of this system before it needed to be secure. And it almost certainly, in the worst case, if you do one of these NLP attacks, it would be trivial to evade. But I'm really curious how well these systems could be made to work, against non-worst case, but someone who just is trying to be nasty, and is really is going to try and evade the system, but doesn't understand, how gradients work for a machine learning model. I think this is a real thing that's worth looking at. Okay, so basically the argument that I'm going to try and make, or I'm trying to make, is that the robustness against practical attacks is something I think we have a chance at being able to do. I think we have the tools now in order to design attacks that work really, really well. We just need to apply them to settings that actually make a difference in order to see if we can try and make things better. Let me give one example of what you might try and do in the black box setting, which is a paper of mine that I worked on with Stephen and David from a couple of years ago now, on the defense side, where sort of, I've spent the rest of this talk sort of talking mostly about the attack side of things that we can make better. But just like, let me talk a little bit about the defense side, about making practical defenses. And the reason I want to mention this paper is because I think it's a nice result. But spoiler, I don't think it works, but no one's broken it yet. And I would like someone to do that. Okay, so what's this defense do? It's a very simple idea. You have some machine learning model that's hosted in the cloud, and you give it an image and it gives you a label. So you feed an image of a cat and it tells you it's a cat. You can feed an image of a dog and it tells you it's a dog. It tells you the cat, dog, right? Like, it's pretty good. It works well in the most settings. All right, so the problem is that, you could feed an adversarial image of a cat and it will give you a label dog. So like, this system is broken. It's not adversarially robust, but it sort of is the best system we have. So that's what you deploy. Okay. So how does the attack actually work? Maybe you have some kind of boundary attack like thing where initially you give it an image of a dog and it tells you it's a dog. And then like you slowly start blending it with an image of a cat until you end up with something that looks very much like a cat, but is given the label dog. These are how these boundary attack sort of things work, is you start with an image and you slowly make perturbations of it until it ends up looking like a cat, but is still labeled as dog. Okay. So the defense here is entirely trivial. All we're going to do is every time we feed an image to the model, we just write down the sort of keep track of the image, keep it in some memory. And then now every time you see queries, you sort of just like write them down. And then at some point you see an image that starts looking, very, very close to like being, a chain of queries that probably something malicious is going on. And instead of giving a label, like you ban the person because it looks like they have made a chain of queries, which any normal user would not have done. And so this is not a defense which is designed to prevent all attacks. Like the defense is going to fail against white box attacks. It's probably also going to fail against transfer attacks. But it's designed to stop one particular kind of attack, a query attack. And I think it does a reasonable job at it. We've designed some techniques in order to evade it in the paper, but we can't break it completely. But I'm not actually convinced that this defense works. I would have to imagine that it would be possible to fool this defense in some way. And I'd like to see someone try and design something that would actually be secure in this setting. Because like these are the kinds of defenses that people might actually want to deploy. Because in practice, people work really, really hard for like every percentage point of accuracy that they can get. And asking them to completely change their entire pipeline to do adversarial training or something like this might be very hard. And so like bolting on these like extra systems to try and increase robustness in some practical settings, I think could be very useful. And so, you can imagine that any of these online content moderation systems work in this way, where the users provide some query and get an answer. And they could try applying a defense like this. But the reason why they don't have to is because no one has actually attacked them. Right? Like no one has really attacked these online systems that exist today. And so of course they're not going to produce any defenses because there's no good attacks. And so I think what I would like to be able to see is like more attacks and defenses on these practical systems in order for us to understand like how good of a job we've been doing in our research space in order to really know to what extent we've been making progress, because progress on worst case perturbations has been hard, but I think that there's a lot of progress we could make when looking at these practical situations. And I'd really like to see this, especially at venues like workshops, where it's not the case that the review is like in this really, really adversarial, for lack of a better word, a situation where people are looking for reasons to reject papers. Oftentimes the workshops are here looking for reasons to accept interesting new ideas. And I would like to see people write more papers in this space. So final conclusion then, I think that the motivation that we came to doing this kind of work in the first place was motivated mostly by either general purpose robustness, and for various reasons I'm just not going to talk about that much, and also by worst case robustness. And unfortunately, it's been really hard to get worst case robustness to have. And so I still think we have a chance to try and get some good results of practical attacks on practical systems, practical defenses on practical systems. But I just, for some reason, we're not seeing that much of this yet. I gave a talk very similar to this a year ago at a workshop, and not much changed. So I'm not hopeful, or I am hopeful, but I'm like not like expecting that we're going to sort of do things all at once. I personally have like changed the kinds of research that I'm doing to try and focus on these practical things. And I hope that I can convince you too to spend time working on some of these things as well. So with that, thank you, and happy to take any questions with whatever time left I have.
Thanks for this talk. Is there any question? Okay. Yun, is there any question for?
There's a question. Oh, yeah, you maybe you need to compare to speak.
Hello, can you hear me?
Yep.
Thanks for the talk. It was really interesting. I had two questions. So there are practical attacks on commercially deployed machine learning solutions like API attacks. I wonder what your thoughts are on that. And sorry.
Oh, sure. Yeah. Okay. So good. So the ones that I'm aware, so entirely possible I missed something, right? Like there are 5,000 papers in this space. So it's if there's something that like is actually sort of very applied, forgive me if I missed it. But the ones that I'm aware of, they attack things like Clarify or Google Cloud Vision, or these like machine learning as a service tools. Like is that what you mean?
Yeah, that's what I mean.
Okay. Yes. Okay. So yes. So I agree. Those exist. In my mind, there is very little difference between like attacking Google Cloud Vision than attacking an ImageNet model on your own device, with the exception of the fact that you can sort of convince the reviewer you haven't cheated. Because like when you attack like Google Cloud Vision or something, all it does is like directly feed your image to the model, look at the answer, and give you the labels back. The difference between that and attacking like some abuse detection tool is that Google Cloud Vision was not designed to protect abuse, but the like abuse detection tool like is the company's attempt at like doing the real problem, and so they may have done other things along the way that we don't know about, other than just calling a neural network and asking for the answer. And so what I would like to see, maybe they haven't, maybe they've done nothing, maybe all they do is take image, classify with neural network, and give label back, and that's literally everything, in which case it should be trivial and someone should do it. Or maybe they've done something else and they've put additional safeguards in place, and then it would be nice to evaluate those in order to see what the robustness of those is. But I think that just moving the neural network from your machine to some cloud machine and then saying that we're calling this a real attack is like better than nothing, but it's like not as real as I would like.
I see. Thank you.
And I think you had a second question.
Oh yeah, I have a second question. So this is more from the defender's side. So let's say I'm implementing a, say some commercially available machine learning product, which say the best example is like identity verification. You take a picture of a driver's license and you try to match it with like a selfie or something. And say I'm deploying this in like some product somewhere. How concerned should I be about white box or black box adversarial attacks?
Yeah, I think this is a good question. I think the only way to know about how concerned we should be about like, ID verification would be to actually try and attack it and see how hard it would be. Right? Like this is, I think, part of the reason like attacks are useful, not only because like they break things, but also because they help us evaluate things. And, I would like to see someone try and look at the robustness of these things. I mean, this is not entirely hypothetical, right? Like in the United States, recently, maybe I've just been rolled back, but like the government had this ID service where, they asked you to take a sort of a video of yourself from various angles and use this to convince them that you are who you say you are. Like, it would be nice for some researchers to have analyzed that system so that we can know, like, is this security theater or is it something that actually is helping? I personally think it probably wasn't actually helping very much in practice, but I don't know. So no one looked at it. It would be like, these are the kinds of things like, we've spent so long looking at the robustness of systems. Why don't we actually look at the robustness of real systems? I would like to see it.
I see. Thank you. Yeah, thank you. That's really informative.
Yeah, I also wanted to say thank you for doing your talk. I really like the structure of covering this path forward. Yeah, the question I had is like, how do you think we can structure benchmarks about practical attacks and how we can connect those to data sets? Because people are really good at taking a benchmark and making it better. I think that's a lot of the success we've seen in the worst case scenario.
Yeah, benchmarks. Yeah, this is something that I think would be nice. I don't know how to do a good benchmark here. So there have been in the past competitions around, especially around black box robustness, that like we're trying to improve things. The challenge with setting up these benchmarks is designing them in such a way that you measuring something real, like you actually are measuring black box robustness, while not relying on just, security through obscurity in some sense. Like you sort of want to both make the defenders commit to something, but then also like disclose what it is that they're doing, kind of, but like not the model weights. And so like I would like to see someone put together a really good benchmark here, but doing that is very hard. That doesn't mean I don't think someone should, like maybe someone should create one of these benchmarks again, like the last one that happened was at this conference, and it was sort of, on some of these things. But like doing it in such a way that it encourages work on the really practical side of things, I don't know how to do well. And I think it's a hard problem. If someone could do it, I think it would be great, but I don't know how to do it very well.
Thanks a lot.
Okay, cool. Is there any other questions?
If there's time, I would also like to ask one.
Sure. Yeah, just go ahead.
Hi, Nicholas. Thanks very much for the talk. I recently finished my PhD in Oxford, and I also my research is very focused around these themes, in particular practical attacks. And I was wondering, what's your perspective on the fact that most of the literature on adversarial examples considers image classification, which is a task it's hard to always imagine this in a security critical scenario, right? And that's why there is some work, for example, on object detection, which is something a bit more, that one can imagine this is a security critical scenario. And I just wanted to see what your perspective was on this.
Yeah, no, I completely agree. I think it would be nice if we did other things too. There's only so many things I want to complain about in one talk. So I figured I'd just sort of focus on the real things. I think if you focus on the real things, you'll also be driven away from images quite quickly. Like the only sort of example that I can come up with where real things matter for images is this abuse detection. And also there's a very nice paper from Florian a couple of years ago on ad blocking. Those are like the only two settings I know of right now where images are what matters. I think if people focus on real things, going to text, going to object detection, malware, all of these other settings where are more traditional security domains, where I agree, I would be nice to see other attacks in those settings as well.
Yeah, thanks very much. I suppose I agree as well.
Yeah, no, again, I would like to see this as well. Yeah, but yeah, thank you.
Okay, great. Thanks, Nicholas, for this talk. Thank you.
Thank you.
Okay, so I guess you want to take over here, right?
Yeah, you to these comments. Up and you can prepare to introduce her. Yeah.
Hey Judy, it seems I cannot hear you. I'm not sure others. Oh yeah,
Hold
I
on
can.
one second.
I can hear you now.
I think you'll be able to hear. I just need to fix the screen
Okay.
on our side. Sorry about that. We seem to have had a power failure.
Take your time. Yeah. In the meanwhile, I can give the introduction for you.
Sure.
Okay. So our next speaker is Judy Hoffman. Judy is an assistant professor in Georgia Tech and a member in the Machine Learning Center. Her research interests include computer vision, machine learning, domain adaptation, robustness, and fairness. Prior to joining Georgia Tech, Judy was a visiting research scientist at Facebook AI Research and a postdoc scholar at Stanford University and UC Berkeley. She received her PhD from UC Berkeley ECS in 2016, where she was a member of BEAR and BDD. Judy, the floor is yours.
Great, thank you. Hi, everyone. I'm really happy to be here today. This talk is going to be more about robustness as a general term and less about adversarial. But what I like to kind of explain throughout today's talk is about how the two are very connected and how we shouldn't ignore the standard, maybe benign or less adversarial forms of ways in which data changes and might cause degradation in our systems. And kind of related to one of the questions at the end of the last talk, I also want to argue for moving beyond just classification tasks. Of course, classification tasks are a great benchmark. It's a nice place to study all of these issues in robustness, but sometimes when you move to other tasks, there are lots of new novel ways in which models can fail, and it's worthwhile to study those. So in my mind, kind of the high level goal of a reliable or robust system is that you would like it to be able to perform the vision tasks at hand as expected at deployment time. Now that's a very vague statement. So what is it that I mean by that? Well, first off, you need to be able to even define what is the expectation. In order to do that, in order to specify how you expect a system to perform, have a set of benchmarks. And of course, we have lots of benchmarks in the computer vision community, but as the focus of this workshop is on robustness, what we really need is more benchmarks and more ways of stress testing systems so that we can understand the true expectations of the performance of a system at test time, rather than the idealized version that we have today. And then we also need different algorithms that help us to be able to withstand as the world changes. So you might just want a system that can work as well as possible out of the box in all scenarios, but the world changes, there's lots and lots of variation. And you need the adaptability or flexibility of a system to be able to cope with these changes as they arise, rather than presupposing access to all sources of variation beforehand. So if we kind of take a step back and think about the standard recognition pipeline, the way that it works today, of course, everything is centered on data. So that's the first step. We need to, before we can even define a task, we have to think about what data we're going to be working with. In many cases, we then need access to labels. Labels are going to define the task. In the case of classification, maybe you have labels like dog. And then we can start training models. And there's all kinds of research into more robust ways to train models with different regularizers, different loss functions. But regardless, we're training those models to be able to predict those labels that we have. And in order to perpetuate this type of study, this type of protocol, we have lots of different benchmarks available to us. In the classification setting, the most famous ones, we have ImageNet or Places. When we're moving on to more complicated localization tasks like detection or segmentation, there's a whole suite of other benchmarks, and these ones range in focus from things like indoor scenes to generic object recognition, maybe focused on people, to even applications like self-driving cars. In all of these cases, though, again, we have this kind of format where we have this large collection of data. Perhaps we try to capture different sources of variation, that we expect to experience at test time. But overall, we're going to carve up this data into a train and test set, and we're going to use that in order to benchmark our progress. And it's been obviously wildly successful in helping perpetuate progress within the field. But now is the time to really make sure that we have a stronger, more realistic characterization of the performance that we expect of our system when we move beyond just this single benchmark. So we need to think more deeply about how we are doing this validation process. And when we get a number like an accuracy or an IOU, we need to think about what are the conditions under which we can promise that type of performance. So if we were to think about a standard benchmark and we take, if you have accuracy, you can plot it improving, you can plot it performance comparing between different systems. But if you have a system that claims to have accuracy of 95 or even 99% in some of these cases, does that mean that that system on that task can be guaranteed to work that well in practice? Of course not. This is a small subset of the true world. And so we need techniques, we need new mechanisms or benchmarks to be able to more accurately assess how well this great model at the end will work. One of the first steps towards that is to acknowledge the types of variation that exist in practice. If we're taking this image, this is from the Cityscapes data set, it's a self-driving data set, and we just want to think about what are the ways in which the world can change. We haven't even talked about adding adversaries yet. Just what are the ways in which the world can be an adversary itself? Well, first off, being able to collect annotations for this type of task is really cumbersome and expensive. So we have to understand that being able to enumerate all sources of variation, collect all of the data, and annotate it is not really feasible. And then we think about all of the ways in which the world can change in this one task. You're outside, so you have to deal with weather changes. You have to deal with the fact that you're going to be driving in many different cities. You ideally would like to have this same vision capability on top of lots of different cars, maybe different sensors, different heights, and so on. So we can try and collect more data to satisfy all of these different sources of variation. And we can try to propose benchmarks that maybe evaluate along different factors. But ultimately, it's going to be an evolving process. You're going to get new data over time. And so just even one static benchmark is not going to be sufficient. Let's say we had only seen a subpart of the world, like we had dominated our data set with sunny images. And now we'd like to see how well our system that performed really, really well on our benchmark is doing at recognizing this image of a road scene that's covered in snow. Well, it fails pretty miserably to recognize the surfaces that have snow on them. And things like recognizing the road or the sidewalk are actually some of the easiest things to recognize in these types of data sets. Yet here it's being confused with things like building. So it just tells us that this subtle change, if not adequately represented in the data set, there might even be snow within the data set, but if it's not represented at a level that is kind of the main source of data, it might be ignored, it might be underrepresented and have poor robustness when these very natural situations arise. Of course, there's been a lot of work looking into all kinds of alternative low-level corruptions that could happen to data, trying to benchmark robustness against these. And there's work discussed at this workshop as well as at the main conference on trying to improve robustness, because systems without taking care to be robust against these sort of corruptions have substantially reduced performance in practice. So with these types of ways in which the world can change, or this motivated by kind of this benchmark on building up a measure of robustness against corruptions, we had a question of how would these corruptions to a visual input vary the performance of a system that's trying to solve a task beyond classification. So in this work called Robustness, we introduced a benchmark for embodied navigation. And we wanted, again, to have a mechanism for measuring some sense of robustness at this task. Embodied vision simulators exist today. Here are two of the really popular ones. And in these simulators, they allow agents to take as input visuals, RGB, sometimes RGB in depth. And from those visual inputs, you're supposed to make decisions like which direction you should turn, whether you should stop or go forward, and so on, in order to solve a particular task. Two of the most common tasks here are the point nav and object nav, whether you're navigating to a specific point, which is kind of an unrealistic task overall, but something that's used to help progress the field, and object nav, where you're asked to navigate to an object, like go to the sofa. So with these tasks, what people did was they would take, again, as input, an RGB image, or perhaps an RGB in-depth image. What's being shown here are those two sensory inputs as the agent perceives them, and then a top-down view that the agent doesn't have access to, which is just used for visualization here. From these sensory inputs, you then make decisions about how to make progress towards your goal. So the agent will kind of move around until it reaches the desired point or desired object. And these systems were starting to perform really, really well at these indoor scene navigation tasks. But they really have a limited version of generalization. So in particular, what they'll do is they will train on a few different simulated environments and then think about evaluating on a held out scene layout. But really, when we're thinking about how the inputs, the visuals change, or even the actuation or the dynamics change, it was very, very small or even no changes between train and test. So that meant that you assumed you had an agent and a sensor that never changed between the training time and the test time. And this is overly limiting because, of course, if you would like this to work in practice, you're going to always be encountering slightly different environments. Your dynamics, your robot are going to change a bit. The visuals that you get as input are going to change a bit. So in Robustness, we, again, inspired by the CVPR' and ImageNet type data sets, we introduced a set of corruptions to these environments, changed them up a little bit from that data set to incorporate a few that we thought emulated what would happen in a robotics environment, like camera crack. And overall, there are 7 visual corruptions and 4 dynamics corruptions. And this is intended to help us to better estimate how well our progress will work in practice. And the idea here is that even if you can benchmark the robustness fully in simulation, it should be a good proxy for how well your robustness is improving in the real world. And this is evidenced by a number of different works that showed that progress within the simulated environments correlated very well with progress in the real world. So it tells us that we can even start improving our measurement of robustness without getting hardware involved. So overall, this benchmark is intended to help us stress test in this setting of embodied agent visual navigation. Here are an example of the visual corruption. So we have things like lower lighting condition, changing the field of view of the camera, adding, of course, things like noise that mimic getting debris on the camera or camera crack. The dynamics corruptions center around either those that would be due to the environment, like a scene level change that mimics friction changing, or two changes that have to do with faulty movements. So like a hardware failure that might lead you to ask the robot to turn left, but it actually either doesn't turn left at all or turns left with a different angular degree than it did at training time. So overall, we have these different tasks, and we use an off-the-shelf agents to benchmark progress here. But really the high-level takeaway is that if you use the 2 different metrics for measuring performance in these embodied agent tasks, which is both just overall success, did the agent eventually make it to its goal, as well as SPL, which tells you a little bit about how quickly it made it to its goal. So if it made it there, you want to have a sense of, did it kind of like wander around for a long time before it actually found it. The clean model, this model that we're benchmarking, it had success close to 100%. So these are new layouts. So this is one of the things that inspired us to actually do this work, is we saw that you're getting agents that are getting near perfect performance, which, as we know, is kind of an indicator that we need to improve our benchmarks, that we're not necessarily capturing the true state of the world here. And overall, this SPL of 83 is pretty high. It means that it's actually finding the goals fairly quickly. So if we look at our different visual corruptions and imagine including those at test time only and trying to see how much does it degrade the system, well, these are ordered in terms of the least to the most degradation in the system. Some of them don't make as huge an impact, like minor changes in lighting. It was fairly robust against that, but changes in terms of defocus or changing the field of view of the camera had dramatic impact. And here's an example of it running. So this is the agent. It's able to navigate to the goal in the clean environment very quickly. In the lower lighting condition, it still succeeds, but you'll notice that the agent is kind of turning around, looking a few different times before it actually makes it to its goal, which means it's going to have a lower SPL. And here's one with motion blur. It made it there fairly quickly. We can also imagine taking an agent and adding in another sensor that itself might be clean. So in this case, the corruptions are only applied to the RGB, but not to the depth images. So we could ask, what if you want to have some sort of robustness through having redundancy in your sensors? Maybe one of them isn't corrupted, only the other is. And then in that case, you have an agent that in the clean case was able to navigate to the point of interest fairly quickly. Again, in low lighting, it was able to succeed. But as we move on to other types of corruptions, very frequently, the agent was starting to degrade substantially or even fail entirely. So we have a lot more examples online if you're interested in seeing some of these, especially the failure cases, because there are a lot of them. But overall, the idea here is that there's lots of different ways, especially as you start to think about vision as a tool or an input to larger systems. There's lots of different ways in which we can think about robustness. Even when you're talking about these small input changes, how do they change the dynamics of this agent? How, if you have lower lighting conditions, is it going to make it fail entirely, or is it just going to make it harder for it to succeed, but it will succeed eventually? So understanding the ways in which these changes are going to impact the overall system is of great importance. The next big piece of this talk is focusing on how we can design algorithms to allow the systems to be more robust, to allow them to perhaps adapt when needed. So there's, of course, you would love systems to work out of the box as much as possible, and we should continue to train with more diverse data sets. We should continue to train with different regularizers, loss functions, making sure that we're not overfitting to the small data sets that we have. But we also want to be able to take these systems and repurpose them as the world changes. So for that, we're going to leverage domain adaptation. I'm not going to belabor the introduction of domain adaptation, but it's just simply that you have access to a large labeled source data set, a data set that has the definitions of a task. So maybe this is your simulated environment or your curated data set like ImageNet. And we'd like to be able to take a model that was trained on this static benchmark and adapt it for use in an unlabeled regime, or maybe a sparsely labeled. But the regime is going to have a visual appearance change. And that change might be due to the weather conditions, sensor conditions, or curation conditions. But in any case, it's going to be a change from where you were training initially. So we can't necessarily rely on the benchmark performance within the source data set to tell us how well the system will perform out of the box on the target. And instead, we'd like to be able to adapt the system. And I'm going to briefly introduce one very common form of adaptation in the literature, which is called domain adversarial adaptation. And the way that domain adversarial adaptation works is that you take a model that's trained using supervision on the source data set, and we'd like to be able to adapt it for use on this unlabeled target data set. And the way that we're going to do that is we're going to attempt to align in the latent feature space the source and target data. We do that by first training a domain classifier to be able to distinguish between the source and target data, and then updating the underlying representation to confuse the feature spaces between the source and target. It's very similar to adversarial learning you would see in GANs, just more operating in the feature space here. So this is a really popular form of adaptation that's still used today, being built on in many different ways, but it has a key limitation that can limit its applicability more broadly in unconstrained data set scenarios. So it turns out that in a lot of the adaptation community, both source and target data sets that people are using to benchmark the reliability of these systems have been heavily curated. And one of the ways in which they're curated is that the source and target data sets have been class balanced. This is very, very common. A lot of the times our data sets that we use to train our models and benchmark our systems have been class balanced. So the problem here is that our target data that we're using to benchmark how well this can work out of the box, it is assumed to be unlabeled. We're trying to say how well can we adapt to an unlabeled set. So if it's unlabeled, we can't reasonably assume that someone has been able to curate a balanced set for us. So now if you think about these marginal statistical alignment techniques, these techniques that just say, can we tell the difference between source and target data? They really assume implicitly that you have some type of a balanced data. And if you don't, you're going to underrepresent and underperform on the rare classes when you do this type of alignment. So the source data set, it's labeled. So even if it wasn't naturally balanced, we can balance it ourselves. But we know that lots of data naturally falls into a long tail distribution, especially once you move into the tasks like detection or segmentation. The positive classes are going to be relatively rare for detection, and for segmentation, some objects are naturally smaller than others and take up less of the image. So they're going to be less rare. A street sign pixel is less rare than, or is more rare rather than a road pixel. So this is going to lead to a distribution mismatch in label space between our source and target data. And so what we really need is we need the ability to adapt even when we have not only appearance changes, but also label space changes, when you have a different distribution of your categories at train and test time. And to demonstrate why this might be an especially challenging problem, I'm going to show you an example that uses self-training for adaptation. So in this example, we have our source data set, this red data set, with two categories, circles and triangles. Because it's labeled, we can train a classifier to distinguish circles and triangles. Now, when we have our target distribution under domain shift, what that means is that the target data is not necessarily perfectly aligned with the source data. And more specifically, it means that there are some examples that are mislabeled. But this is what leads to the performance degradation overall. So there's examples that are mislabeled. Now we think about using a self-training approach, which is something like doing an entropy minimization or a pseudo-label training. And when we have that, what happens is we end up reinforcing the errors that already were experienced by this source model. So this has the end effect of trying to increase the confidence of the current labeled predictions, which is basically like tightening these clusters. So we're not necessarily improving the model's performance on the examples that are already mislabeled. And this in itself, we viewed as a limitation due to using an adaptation on all observations. So if we indiscriminately look at the predictions of an example and use that, incorporate it using a pseudo-label or entropy minimization into our training, that in itself is going to lead to an unstable learning criteria. So instead, what we proposed was to come up with a way to estimate the reliability of an unlabeled instance under a given model. And once we have that, we can use selective entropy minimization. Oh, we're going to leverage some prior work that uses augmentations of images as a way to estimate the reliability of a sample. So this work from 2019 used it to estimate both adversarial examples and found it to be decently effective, as well as natural errors that would occur. And then, of course, in general, people have found that training with multiple augmentations and asking for invariance to these augmentations is a very effective self-supervised learning technique. We're not going to be using this type of self-supervised learning. We're going to be using augmentations as a selection tool. So the key idea here is that we're going to use predictive consistency across multiple views of an image in order to estimate the reliability of a sample. So ideally, we would be able to identify certain instances, like maybe these instances, to be reliable here. And if we can identify them correctly as reliable, well, then we can safely and reliably increase the confidence of those instances such that everything is aligned on the right side of the source hyperplane. In a few more details, what we do is we train a source model using some type of what are your favorite supervised learning loss. And then we're going to pass our target data, which is drawn from a different distribution, through that source model. If you pass it through once, you get some output. You don't know if it's correct or not. So we're going to augment it a number of times and then pass each through in order to get multiple predictions for this single image, with which we can do our selective entropy loss. Selective entropy loss is going to take in those different predictions, and it's going to do a very simple consistency checker. You can use something like majority vote or unanimous vote here. If these predictions are consistent, then we can deem it to be reliable and we can safely minimize the entropy. In other words, maximize the confidence on this sample. But if it's inconsistent, and this is the key piece, is that we're basically filtering out these inconsistent samples. The simplest thing you could do is just a pure filter, don't pass it through at all. But what we found to be a little bit more effective is to actually maximize the entropy in this case. What this does is it pushes these inconsistent samples closer to the boundaries of the decision boundaries, which allows it to be more likely that your updates to the confidence samples will label flip these and result in positive updates. So overall, I'm just going to go through result very quickly here. This is going to be on the mini domain net data set. We have a lot of different results in the paper if you're interested, but also benchmark how well this performs as you change the imbalance factor, meaning the long tailness of the distribution. But overall, on this mini domain net data set, we can benchmark performance. This is a classification task, so we're looking at accuracy on the y-axis. These results are averaged over a lot of things, 40 categories, 12 shifts, just showing them for simplicity here. For reference, the source-only models, so doing no adaptation, got around 66% here. These groups of methods are distribution matching methods, so these are not necessarily taking into account anything about the label distribution shift. And you'll notice that many of them have either on par with source or slight improvements here. If you just took into account label shift and forgot about appearance shift, you don't do very well. If you consider both together, you start to do a little bit better using either an approach that's based off of a relaxed distribution matching or self-training, but using confidence for pseudo labels instead of our selective entropy here. Or an entropy minimization that's also training with self-supervised learning and also using mix-up loss. So kind of like lots of different things. That one is doing the best in StPDM. But here we have ours, which was able to outperform these prior approaches across a number of different shifts. In general, at the time of the publishing, I'm sure there's many new ones now, it was beating the state of the art in 27 out of 31 of the tasks. But kind of the interesting thing here is that it's a very simple idea. There's not a huge amount of bells and whistles to this approach. It's really just using entropy minimization or maximization, but it's using it on top of only reliable instances. So this idea of selecting those few instances. In the interest of time, I'm going to skip over these results. I'll just say that we have extensions that deal with semantic segmentation, as well as a very recent archive paper that instead of using random augmentations for measuring consistency, uses an attention condition masking approach to generate different views of the image that we find to work quite well, especially on top of self-supervised learning techniques, as well as visual transformer models. So overall, in today's talk, I've kind of touched on a few different things, but at its core, there's two big pieces. I'm basically advocating for broadening our definition of how we benchmark robustness, thinking about other tasks beyond classification. I showed you one work that had to do with an embodied navigation. That was the robust nav work. But then I also want to think about robustness and reliability when we're talking about performing down the road tasks like adaptation. So not necessarily adapting on every instance at once, which might lead to reinforcing errors, which might degrade the performance of the model, even as we're trying to make it more robust and reliable in new circumstances. Instead, thinking about what are the conditions under which we can safely use these algorithms in order to increase the reliability of our systems overall. So with that, I want to thank my lab who did all this work. I tried to highlight people as I went through in the bottom with their citations, and you're welcome to check out those papers if you want to hear more about any of these works. Great. Thank you. I can take any questions if there are.
Thank you for your talk, Professor. I learned a lot. But I have a question for the benchmark. To talk about the robust navigation.
I guess we can have a disconnect for a moment. Oh, okay.
Sorry, can you just repeat the question really quickly because I got distracted by this? So you're talking about the robust nav work? And
Navigation, right? What is the difference? I feel like many times the robust vision can be directly applied to visual navigation, right? And what is missing or what is new for this benchmark that waiting for us to explore? Anything additionally that cannot be done by this approach, but that we need actually can navigate in order to solve this navigation task.
I think that one of the difficulties is if you don't have the benchmark, then it's hard to think through all of the scenarios that might go wrong. So for example, the ways in which it fails, it's not necessarily missing it entirely, but it's taking longer to access, longer to find the point. Also, when we are designing the corruptions that might happen, we change the set of corruptions. We introduce things like spatter or camera crack, as we tried to think through what would happen if you're in an outdoor scene and navigating around. What are ways in which the camera might, even when it's deployed, change? So that's one of the, so basically behavior of the system overall is you need to have the benchmark to characterize it, but then aside from that, you need to have the application in mind sometimes to think through the ways in which the visual appearance might change.
Yeah, do you think the robust policy will be potential direction?
Yeah, absolutely. I think the two are inherently intertwined. So, I mean, there's actually been quite a lot of work on this recently, and some people are trying to see whether or not you can induce robustness by having a combination of robust vision and then robust policy kind of done separately, which to me, that modular approach seems like it might be more viable. It's easier to validate than to do it all end to end. But I do think that you still need to evaluate it end to end, whether or not your solution for robustness is modular.
Thank you.
Sure.
So I think in some of the earlier slides you showed.
I don't think they can hear you.
think some of the earlier slides were showing how some of the corrections that you designed, like, so I was just wondering, like, if you come up with like some kind of new corruption process that you find to be like significantly degrading, and would simply like adding that corruption into your training set be like effective in order to like reverse that attack, like kind of like online adversarial learning, and like, is that like in general like a good strategy?
It's a partial strategy, I would say. I mean, it's the same argument of if you're missing that weather condition, what if you train on that weather condition? And I think that we should be doing both. I think that we should be trying to integrate more diversity in the training data, but we should also be holding out conditions so that we can reasonably benchmark what will happen. New things happen at test time. I think it's inevitable that new things will happen at test time. And we have actually in the appendix of that paper some experiments where we incorporated some set of the corruptions at training time and show that you can get you can improve the robustness a bit, but you can't recover to clean performance. There's still a gap there. Yeah.
Thank you for the great talk. In my experience with users, they would love to have robust systems, but they're very reluctant to use performance or accuracy and so on. I was wondering whether you could share your experience with respect to that and whether this is around or ready.
Yeah, it's a great question. Overall, I completely agree. I think that we have to think about the balance between the two. And I didn't talk about it in today's talk, but we have a number of different projects that look at ways in which you can kind of improve the out-of-the-box robustness, but still retaining in-domain accuracy. And personally, what I think is going to end up being the right approach is that we're probably going to have a large model that has basically specialized subcomponents that are used if they're relevant or ignored if not. So you're going to get robustness through a core part of the model that's invariant, but maybe and a generalist, but maybe not performing quite as well in certain specialized scenarios you've seen before. But in order to accomplish this goal, we're going to need the ability to rapidly and reliably switch between these different parts of the model. So I think that's where innovation needs to happen.
I really appreciate the topics that you covered, particularly for the robust benchmark and such. You have visual perturbations in the image. So I want to know how well those perturbations represent real natural perturbations. Because I've worked with, say, synthetic rendering rain, all these things.
Yeah.
And typically they don't quite generalize and not necessarily real images.
Yeah, I mean, so I think that's a fair point and a good point to bring up, which is, of course, we're training in simulation because we hope that progress in simulation is going to perpetuate progress in real deployed systems. But it does still need to be verified, that step from sim to real. I think that a lot of the reason why some of this particular problem statement, I kind of had that one slide in there that showed that people have said that progress in simulation on these indoor scene navigation tasks correlates very well with progress of the system and in the real world. But I think that might be because these are fairly simplistic environments, right? These indoor scene navigations. So I think that once you move into outdoor scenes, they might have to do some differences. But overall, the design of the corruptions here is attempting to mimic things that could occur in real world.
Yeah, completely on that point. Particularly, or some of the, say, on the weather perturbations stuff, particularly hard, especially on, say, degradation of your LiDAR sensors across snow. But one of the things I was wondering is, do you see maybe a future direction of this being, should we collect large scale, say, adverse weather condition, weather data sets, real data sets, instead of something?
Yeah, I mean, I personally think we should do it all. I think there's a place for simulation. I think simulation can be very helpful as long as you have a way to make sure that what you're learning in simulation does not overfit to simulation. So that's a challenge in itself. But of course, there's probably even a whole workshop here on sim to real challenges. But it's oftentimes hard to collect in the real world every scenario, and you might be able to generate some scenarios, especially safety critical, like crashes or things like that type scenarios. And so I think that having simulation, collecting larger data sets with more diverse conditions will be helpful. But as soon as you start to incorporate the diverse conditions, it's like, what are you going to do? It goes back to this previous question. If you start incorporating lots and lots of foggy conditions, you might degrade your sunny conditions. And so you have to, there's a balancing act that has to be thought about here. And right now, our solution of kind of like pool all data together, train all at once, one large model that processes every image no matter what the same way, doesn't really seem like the right long-term solution.
Exactly. Real appreciate the answer.
Yeah. All right. Should we pivot? Is it time for the next speaker?
Oh, yeah, I can hear you.
Oh, okay. Oh. I didn't know who to speak to.
Maybe next year. Yeah. Okay.
Thank you.
See.
Not really sure what this hybrid protocol is like, but thanks everyone. I guess we'll have the next speaker.
Wait a moment.
Okay. So meanwhile, I can give the introduction of Alan here.
Wait a moment. You want to introduce Alan first, or I can
Introduce me while you're setting it up. Saves time.
Okay. Okay, so our next speaker is Professor Alan Yu. Alan is a Bloomberg Distinguished Professor of Cognitive Science and Computer Science at Johns Hopkins University. His PhD on theoretical physics, supervised by Stephen Hawking, and was approved in 1981. He was a research scientist in the Artificial Intelligence Lab at MIT and the Division of Applied Science and at Harvard University from 1982 to 1988. He was served as an assistant professor and associate professor at Harvard until 1996. He was also at UCLA before joining to Johns Hopkins. Alan also have received the Mar Prize and Hermitage Prize. Alan, the floor is yours.
Thank you very much. Can you hear me?
Oh yeah, I can hear you.
Okay, so thanks very much.
It seems the audio does not work very well. Can you come closer, maybe to the computer, so we can hear you more clearly?
Can you hear me now?
Yes.
Can you? I can't hear myself.
I can hear you.
Okay. How about now?
Yes, but we cannot see the slides.
Maybe just.
Well, did you put them onto that computer? In which case,
Yeah.
why don't I use that computer?
You use this computer, and the audio is from this.
Yeah, but can he see the slides?
No, we cannot see the slides.
You can't see the slides.
Oh,
I think you use my slides on that computer, I think.
you have Zoom. Maybe you can share a screen. Can you see the slides now?
Yes, we can see the slides. And also, okay, yeah, good. Yeah, maybe you can play the slides and in the full screen, so we can.
Okay. So you can see that slide. Can you see
Yeah.
the slide?
Yes,
Uh,
yeah. Everything
actually,
works.
Full screen.
Mhm.
Okay.
Okay, sorry about that. So the title of the talk is intended to be provocative. Mismeasurement of AI, need for adversarial examiners. I think some of the themes have come up in the talks earlier today. And perhaps I should, and let's get into the topics, adversarial attacks. You know, there was the idea of devils and angels. Original attacks used were imperceptible. Small perturbations to the images can make deep networks fail. That was the devils. Defenses against the attacks can make the algorithm stronger. That was the angels. But I think that's only a very small part of what's happening. And I personally don't care at all about, you know, nasty people trying to mess up my algorithms. If they can mess up my algorithms, it's because my algorithms are bad in the first place. I think, you know, I don't want to, you know, the word adversarial means somebody is really, you know, some nasty person is trying to make your, you know, your algorithms not work. That's not how I think about it at all. I think it's more that this is, you know, that we're not actually testing our algorithms properly in the first place. If we did, if they passed all the sorts of tests we all put on them, then, you know, malicious people could do whatever they wanted. It would not matter. Okay. So I think we need, you know, in terms of adversarials, I think we need really stronger attacks. You know, we call these things devils. These are not devils. These are tiny little, you know, I don't know, you know, they're not devils at all. We need far stronger devils, etc. We need them to stress test the algorithms, and then we need to see if standard deep nets can defend against them. Okay, so I think a buzzword would be without stronger testing, we won't get strong AI. That data-driven methods like deep learning have made, and they'll continue to make enormous progress. It's a really exciting field. It's led to, you know, it's constantly developing novel ideas and so on. But I think that they have limitations, and these limitations are not probably appreciated because of the way that we test AI, by the mismeasurement of it. And the stronger ways we should test it include things like domain transfer, things that have been mentioned before, out of distribution and out of target, and more controversially, I'll argue for adversarial examiners. Now, here is stop and rethink our evaluation methods. I think this came from a talk by the head of Google, so not Google, sorry, Tesla, Karpathy, saying that, you know, despite lots of efforts, they still couldn't find stop signs all the time, which is problematic since stop signs are intended to be found. And as someone who drives a Tesla car, I can testify to that. But basically, I think that the standard evaluation measures that we have assume finite size balanced annotated data sets, BAD for short. And then we have a loss function. If our loss function, you know, if you can find an algorithm that minimizes the loss function nicely on these data sets, we think it's going to work well in the real world. But I claim is that the data sets, no matter how big, are not really representative of the real world, because the real world is far more complex, infinitely complex. Now, as someone who's also motivated by human vision, I have to defend humans, and claims that AI can outperform human observers are flawed. AI algorithms can exploit biases in a data set that humans cannot, because these are biases, they shouldn't be there. The deep network can exploit them. And so if you look at this slide here, which is quite famous, showing you that a few years ago, it looked like deep networks were outperforming humans. It frankly somewhat irritates me, because you know, first, it's actually the people who study human vision, it's been known for a very long time. There's a whole lot of work called ideal observers, and you can get, if you choose particular domains, you can get machines that can outperform humans enormously. That's because the humans know, in those cases, the ideal observers know all the statistics of the data, they can exploit it in their algorithms, the humans don't, so the humans do worse. And I feel that the claims that the AI is outperforming humans, you know, deep nets are outperforming humans on ImageNet is really just an example of that. The AI algorithms know the images in ImageNet, the humans don't. So is AI superhuman? Maybe, perhaps, but we won't know unless we test it properly. So mismeasurement of AI, the way we evaluate AI algorithms is flawed. So the sort of basic technique we use, standard machine learning that I think everybody does now, 20 years ago, and I'm an old man now, or almost. You know, I remember when we didn't evaluate algorithms those ways, so those methods came in, they were reasonably good, but they are based on certain underlying assumptions. Assumptions I used to teach in courses. You know, you assume that the training and the test data comes from the same underlying distribution and that they're balanced, random, etc. The mathematical theorems about this, which I used to prove in courses and then gave up proving because I'm not sure anyone cared too much about it. They're quite nice mathematics, showing in if that's the case, and you train on a big enough data set and test on a big enough data set, then that guarantees that your algorithms are going to transfer to other images that come from that underlying source. But those mathematical conditions don't really apply to the real world due to its huge complexity, combinatorial complexity, etc. The data sets are not big enough to be representative of the real world. In most cases, we also work on medical images. In medical images, the data sets are big, the complexity is hard, but arguably you're not getting to combinatorial, you know, you haven't got the enormous complexity that you have in the real world. But apart from certain special cases like that, the data sets aren't big enough to be representative. And the point there is that current evaluation methods do not guarantee that your algorithms will work in the real world. That's one problem. The second problem is that they favor regression type methods like deep nets instead of alternatives. So deep nets are trained for the test. They do well on the test. At one of the earlier talks, somebody was mentioning why hasn't there been a lot of improvement in algorithms against adversarial attacks, comparing that to improvement in other parts of, you know, say in generative models, where they've certainly improved enormously in the last few years. And one reason for that is the way the algorithms are evaluated. To get a paper into a conference, you need to show that it does well on these types of measures. To get grants accepted, you need to show that you've done work that gets them accepted on these types of methods. These types of methods, standard, you know, regression methods like deep nets are very good for, you know, so in footballing or metaphor, you're playing a game on somebody else's home turf if you're trying to develop algorithms that can be alternatives and that might actually be better in the real world. So I think there is a problem there which hampers research. So over-reliance on context. So here's a recent example from this conference. And the first author, I think, is in the room, or I saw him just outside. And here is a vision questioning answering algorithm. And so the question is, what is the dress of the woman playing tennis? And on the left-hand image, you know, the algorithm is correct. It's an orange dress. In the right-hand image, what do? You replace the tennis ball by a football or a soccer ball if you're American. That's all you do. It's nowhere close to the woman at all, nowhere close to her dress, and yet the VQA algorithm now says that her dress is white. Why does that happen? We've got no idea, I guess, and that's part of the point. So this is one of only many examples that if you're at the workshop, you've probably seen where you can make small changes to the image and you can get completely, you know, you can get an algorithm to make completely the wrong type of answers. Swap mix, so we show Gupta et al. Just balance, you know, swap those features around, and you know, 45% of the time questions, a typical VQA question answering algorithm is going to make mistakes. Now you can also use that to improve the algorithms, but I'm not going to talk about that now. And you know, you can do that to almost any type of algorithms. So how to test them more strongly? Well, I think there are a growing number of ways, and you know, we heard, we here, as we heard earlier this afternoon, you have new data sets being put up, new types of tasks being put up. So that's important. And the key idea is, I think, really needing to develop algorithms that have better understanding of the data and could really generalize outside the training set. So out of distribution testing, the test samples come from a different distribution than the training samples. Domain transfer, you learn the data on samples from one domain, you test it on another one. Out of task testing, the algorithm's trained to perform one task, but tested to perform another. There's a range of those types of methods, and this is appreciated, outside the vision community. Bernard Scholkoff, who made his reputation with support vector machines, which were very much a method that worked on balanced data sets, etc., has been working on causal learning, and has, advocated out of distribution testing as a way of showing you've got causal algorithms that really understand the data. So more radically, adversarial examiners are something my group has been proposing. And the point here is that instead of testing algorithms by just random samples, you test them by a sequence of samples. And so a sequence of stimuli where each stimulus is selected, taking into account the algorithm's response to the previous stimuli. Okay, not just random samples, but you can ask a series of questions to the algorithm, and each question can be informed by the response of the algorithm to the previous question. And the instantiation for doing this is to use reinforcement learning, which can specify a control policy for selecting the next stimulus. And they can be more effective than random sampling of setting over the space of stimulus, but even more importantly, really, they can expand the set of samples that you're testing to a perhaps infinite set. Any finite data set, you've got n examples you can test on by modifying the stimuli in the way the adversarial examiners can do. You can change the stimuli, you can generate enormous number of them and test on all of those. Because in a sense, the key problem of the standard methods we're testing is that we don't have, our data sets aren't big enough to test them rigorously, and because we can't test over an infinite number of samples, not if we're doing random testing, but if we do testing where we can have a search policy that can navigate you through this space, infinite space of tests to find the ones that are hard for your algorithm, then we can. So I'll give a few examples, 3 examples of work on this. This is the first paper we had by Michel Xu in 2020 in III. The idea is you want to recognize objects from different viewpoints. The stimuli were synthetic stimuli. You use ShapeNet objects, and you can rotate them. So you've got a sort of infinite space, viewing space of them. The search policy was reinforcement learning. And you could take algorithms for classifying objects and conventional testing of them by random sampling, shown here on the bottom with this sort of blue curve, doesn't detect any problems at all. If you detect them adversarially with this sort of adversarial examiners, you find there are viewpoints where the algorithm starts confusing the 2 objects. Initially, and this is classic reinforcement learning, you're sort of exploring the space, you're not actually, with this orange curve, you're not actually finding any problems. But at a certain stage, you start finding that the algorithms start failing under certain conditions when the viewpoints start becoming similar, and then you could rapidly see that the algorithm is making mistakes. One on real images was called patch attacks, which is like, adversarial attacks with patches, which have been around for several years. These are attacks which are visible. They are not, but no human would actually get confused by them. And here, again, you train a reinforcement learning algorithm for search policy. So you can start out with images like of a car, say. I mean, you just take them from whatever data set you've got, and then you can modify them by putting in patches from a dictionary, allowing you to generate, you know, an infinite number of images, essentially, and the algorithm searches over that infinite set of images to find the ones that can cause your algorithms to break. More technically, this would be a, you know, this is a targeted black box attack on a deep network trained to do classification. And these attacks are targeted, which means it's pretty hard. You're trying to turn a car into some specific object, and they're over 90% effective with fairly small patches. You can turn the t-shirt into a pretzel by putting in this little patch here. You know, you can turn the scoreboard into a file salamander and everything like that. So that's another example. A third example is work in this conference is a collaboration with Boston University ourselves, Nathaniel Ruiz, who I think is somewhere in the audience. Yes, hi. So you can ask questions about this to him. But the thing here was addressing the issue of face recognition. And as you know, this has been a fairly controversial topic because algorithms for face recognition seem to have rather embarrassing failures on people from certain, ethnic groups, etc. Okay, so how can you think of addressing that from this type of perspective? Well, you can have computer graphic simulators for rendering faces, and you can render various properties of them. You could potentially change shape, appearance, texture, and various other things, and you can control this. So by generating the faces, you've got an almost infinite set of faces that you can generate, and you can apply the adversarial examiner strategy, or more sophisticated variant of it that Nathaniel developed, to essentially search over these types of configurations to see which cause the algorithms to start failing. And again, the findings are somewhat similar to what you would find in Michel's Shoes algorithm, that if you test the algorithms with just random samples general, well, you don't really find much weaknesses in them. If you test them adversarially, where again, each stimuli, you don't just pick a stimuli at random, you can start by picking it at random, then modifying it, asking a series of questions to the algorithm so that you find a stimuli that the algorithm doesn't like. If you start doing that, then in orange, you start finding you've got ways of breaking the algorithm. So the adversarial algorithms can search for the worst case, or sort of the worst cases, if you like. There could be regions of the space where the algorithms work really badly. They can be efficient. They could work in spaces where random sampling is impractical, and they can explore infinite space of possible stimuli instead of just training on a fixed test set. I guess intuitively, this is how professors test their students, or some students test their professors, by asking them a series of questions where each question depends on the answer to the previous question. You don't test somebody's knowledge by asking them a set of random questions. You ask them a series of questions where the results, the second question depends on what the person said to this first question. This is a common strategy to sort of do exponential search, the game of 20 questions and so on. And so it's just saying, shouldn't we test our algorithms in this way? Now, as somebody motivated by human vision, I'm fairly sure that if you test the human visual system by doing this type of thing, it's going to work pretty well. It's going to be very hard to break it in this manner. Possible, but very hard. But I'm betting that if you test any computer vision algorithm at the moment, it's going to be broken by these types of tests. Maybe, probably not by the adversarial examiners we have now, and probably, but by the adversarial types of examiners that we can create. It's also, if you think about it, this is how we test, mature technologies. if you have a software system, you don't run it at random. You try and break it. You try and find the configurations that cause the software system to break down. And similarly, if you want to construct a new airplane or a new car, you would certainly try and identify its failure modes and stress test those. You do not do it just at random. And so I think the machine learning community, for reasons that made lots of sense 20 years ago, sort of got itself stuck into the mold of thinking, yeah, let's test everything randomly. And you rely on these nice theorems, etc., and they're wonderful, except they don't apply in really complex situations. How does AI relate to imperceptible attacks? So imperceptible attacks, of course, have been addressed, and there was nice work by Alexandra Madry's group that formalized this in the min-max formulation, where standard machine learning minimizes the loss function on the data set. Min-max allows essentially you to make the data set bigger by, for every image, you create an epsilon ball of other images, etc. And instead of minimizing the loss when you're learning, you minimize the loss over the maximum distortion that can hurt your algorithm, etc. So the adversarial examiners can have similar min-max formulations. It's just that the modifications you put to the images are not just small perturbations. They could be patch attacks, they could be all other types of things, etc. Are adversarial examiners too tough? So on one hand, maybe they should be, because AI is no longer an academic discipline. We want to make sure that algorithms work well under real world conditions, so tougher testing is essential. I was asked this by a Stanford student who said, well, actually he didn't say it, I paraphrased what he said, is this like the stereotype of German over-engineering, where you spend years making one piece of something really, really good at the expense of the whole system? And possibly, but I think unless we test our algorithms in this way, they're going to break down sooner or later. Maybe not now, maybe not on certain applications, but essentially, effectively they won't. So I think as a community, we should aim at worst case performances over the infinite space of stimuli and not average case over finite set. We should be trying to develop super devils and enable us to correct them. And the conjecture for myself is interpretable AI algorithms will be easier to correct than black box, because you've got a black box algorithm. How do you correct it? You just give it more data and hope for the best. Now here I have just a few slides of some work that my group did, which is a way of defending against these, if you call them defenses. If anything, actually, my views on these sort of adversarial attacks were partly motivated by the fact that this type of work, we found it hard to get it published. So if we take compositional nets, and we've had several papers on these are robust to patch attacks, and they started off because we wanted to have algorithms that could be robust to occlusion without being trained on occluders. So here is the occluded data set. Most objects in the world were occluded. They may not be occluded in ImageNet, they may not be occluded in big normal data sets, but in reality that happens. So we have a couple of papers showing that we could develop algorithms that would be robust to these occluders. That counts as out of distribution testing because the test data has different properties than the original data. Compositional data, it can also, and this is a paper that's going to appear in this conference, and this is out of task testing, that the compositional models can learn boundaries of objects without any extra supervision, just being trained on classification. And they can also do other forms of domain transfer between different weather conditions. I'm not saying that other algorithms cannot do these things. I'm just giving the comp nets as a proof of concept that you can have algorithms that can perform as well as deep nets on the standard data sets, but can also perform well on these types of tasks. And I don't want to call them super angels because I'm only too aware of their weaknesses. And we're probably not doing very many more of them in a particular form because of that. Okay, but now robustness to adversarial examiners, at least to adversarial patch attacks. So you take the patch attacks that were developed, as described earlier, you put patches in, you can cause deep networks to make mistakes, over 95% mistakes, targeted attacks. You put them into a COPNet, and the COPNet is order of magnitude or orders of magnitude more robust without changing it. This actually meant that the paper was not accepted by CVPR because they said the COPNets have already been published, and so what? But for me, I thought this was a nice, a nice result. Okay, so they have these capabilities. Why? Why are they robust to these, etc.? They have the same supervision. They're generative. They have a generative model of feature vectors, but they also learn certain internal representations of viewpoints and parts. And since they're generative, they have models of how the data, or at least how the feature vectors can be generated, and you can supplement that with a model of saying, of general properties of the world, that an image could be generated by an object, or there could be something in front of it that could generate a subpart of it. You can add an outlier process to this that makes them robust to all these properties. But essentially what happens is that these have models of the spatial structure of objects. They're not as precise, I wish they were, as saying for a car, they know here are the tires, here are the tires, here are the windows. They're moving in that direction. They don't have it as well as I'd like them to have, but they do have a certain amount of that knowledge. They have, for example, the type of knowledge that a small child probably learns during development. When children learn, when infants learn images, they don't do it by giving samples. They learn by taking objects, picking them up, playing with them, trying to eat them, etc. And they have three-dimensional models of the structure of the objects, within their heads fairly soon afterwards. This does not happen with standard deep network algorithms or transformer algorithms or anything like that, as far as I know, because there's nothing to cause those algorithms to learn those types of structures. The COPNets have it to some extent because we essentially put it in by someone supervised learning things, but it's only a starting point. It's not the sort of knowledge about the world that humans would have and develop during development. And I have to say, I cannot see that if one just takes deep nets or transformers, all those wonderful things like that, throws in language, etc., that the models could start learning that structure. It's a challenge for them. Maybe they can, but unless they can, I cannot see how they're going to survive the types of attacks that I'm proposing. So getting back to summary, mismeasurement of AI, adversarial examiners, we need to test our algorithms more strongly to ensure they work in real-world conditions. The current evaluation of measures favor data-driven regression-based techniques, and they fail to predict performance of AI algorithms on the real world. Out of distribution, domain transfer, out of tasks are steps in the right direction, but I think adversarial examiners, methods of that type, methods that don't just test by random samples, that test by asking series of questions, are going to be tougher tests. And I'm pretty sure you could break any existing algorithm using those methods. And you don't even need to know the interior of the algorithm, you only need to know, as a black box. So I don't mean that we should, and to be too radical, you shouldn't retire all the other stuff. Those types of testing are good. They've led us, those types of testing and balanced data sets over the last 20 years have led to computer vision achieving a level of performance that we certainly hadn't got by the start of this century. But I think we need to go further in terms of testing. We need to test far more strongly. We need to develop super devils. Super devils are our friends, and they will motivate us to construct super angels. But if we don't start testing like this, we'll get stuck in perhaps local minima where we're testing with current methods. We're going to end up with wonderful regression-based techniques, but we won't be solving the real problems of vision. Thank you.
Thank you for the talk, Professor. I'm Chen Mao from Columbia University. Also work on the adversarial field. So I have a kind of basic question. So what is the reason you care about the super level examples? Because they are super hard to find also, but even with very strong in optimization algorithm. So it's very unlikely to happen in real world. So is there any reason you could care about those super levels? Thank you.
I don't think they are that unlikely to happen in the real world. Well, I have two answers. Yeah, one is I don't think that that's really unlikely to happen in the real world. The second one is I'm pretty sure humans could deal with all of them, and human visual system is the best one we know of, I think. If so you can put these things aside by saying, okay, these are corner cases, they don't really happen. I talked to some of my ex-students who are going to be billionaires somewhere in startup companies. They have big, huge data sets. They say, we still get corner cases, however big the data sets get. The corner cases, the unlikely things, they still happen. That was what what Kapathy at Tesla said. So they may not happen very often, but they happen fairly frequently, I think, in the real world. They may not happen in ImageNet, they may not happen in COCO, they may not happen in these data sets that we use. They probably certainly don't happen in CFAR or MNIST. But I think, I think they're underestimated because of how we set up the data sets. When people set up ImageNet, people thought, hey, there's no chance in the world that AI is going to solve these. They did, but maybe if she'd known, she would have set up ImageNet a lot harder, etc. So that would be my answer.
I have a follow-up question.
Yeah.
Exponential exploration.
Okay.
So even now, the training accuracy on natural examples are not 100%. So it means that naturally there's corner cases. So why should we care about adversarial corner cases, even the natural examples are not 100%?
I mean, you're saying that we shouldn't care about them until we can get 100% correct on ImageNet?
Yeah, kind of. So they first saw natural accuracy, right? And then we go to the super level.
Okay, you can say that, but I mean, that's really what we've been doing over the last few years, I would say. I think I irritate my students a bit by, they're saying, hey, we got 2% improvement on our deep networks. And I say, well, 10 years ago, hey, we would get 7%, when deep nets came along, you get 7%, 10%, 15%, and now people are struggling to get small improvements with a far bigger community, with far more computer resources, and with an incredible lot of clever people in the clever people and future clever people, no doubt. So I think the injury is also it's the classic professor thing. You're teaching to the test. If you teach someone to the test and you make the particular test harder and harder and harder, and they're not representative of the real world things, you're not really gaining. Mathematics in England, Cambridge University, where I came from, they used to have a tricourse. It used to be incredibly hard to do it. It was like playing elaborate chess puzzles. And then they modified it because I realized, okay, people who can play elaborate chess puzzles don't really become very good creative mathematicians. It's a different skill. So the trouble with that is I think we will we'll become better and better at solving the wrong problem, to put it bluntly.
Thank you very much.
No.
Great, so thank you.
Thanks.
I was wondering whether you have any views on how to incorporate the corner cases found by the super engines. Is it through plain learning? Is it through other methods, cross training? Is there anything in particular you have in mind, or is this going through consolidated techniques?
Well, I guess I'm old-fashioned, so I believe we need to have representations of objects. And I think the CompNets were tended to get towards that. I think I may be misunderstanding, but I think if you just have more and more tests with more and more examples and train the algorithm on more and more examples, it's not really going to help. I mean, on the adversarial examiners that we did there, we, certainly the patch attacks, we did train the algorithms on more and more examples. It didn't work. I mean, I think for any particular type of attack or adversarial examiner, there may be ways that you can come up with a quick fix for that particular type of attack, etc. But I really believe that, like human vision, we need to have algorithms that have knowledge of the underlying structure of objects, including geometry and parts and relationships between parts, things that are a bit out of fashion now, but I think will, as in many things in computer vision, in my experience, will come back into fashion. Somebody said we go round and round in circles in computer vision, maybe in the helix, because we get better each time we go around and rediscover the old ideas. But I think, I don't see that happening out of the more general deep network type methods.
Is it fair to say you had some sort of neurosymbolic mechanism?
It's some sort of neurosymbolic, yeah. I mean, it's probably no neurosymbolic method that's actually been described in those terms, which is why I didn't use the term. But yes, you've got to have some combination of the neural features and some knowledge of the structure of the objects, I think. And, for motivating this, I think we ought to, if I talk to some of my students, I'll say, yes, Alan, being polite to me. And then they'll say, well, we need to get papers into conferences, we need to get jobs at Google or Amazon or something like that. So we need publications, so we need to do better on ImageNet or something like that. And yeah, that's partly my concern with, your question earlier. We're not necessarily solving the right problems. We're having an illusion of progress. And if we're more aggressive with the way we test algorithms, I think we will find their limitations sooner and we'll defend against them. But I think it's got, I can be wrong. I've been wrong many times in my career, but I don't think we'll get them by just modifying deep networks or doing transformers or training DALI type systems. Those may be helpful parts of it, but I don't think they're nearly adequate enough. So if
Is there any questions from online? Tom, can you hear me?
No, we don't have a question here.
if that silenced everyone, maybe that's good, but yeah, it's probably extreme views, but I hope it gives people a chance to think about these things. And I think workshops like this are really the right forum for doing that, I think. Yeah, okay, thank you. Okay.
Okay, Yingwei, should I share the screen?
Yeah, you can share.
It seems that you need to like disconnect Alan's computer to this. first because I'm not allowed to share a screen while others can share it.
Okay, let me do that.
Okay.
Let me figure out how to. Wait a moment.
Okay.
Share a screen now.
Okay. Yeah. Cool. Can you guys see the screen?
Yeah, we can see your screen.
Okay. Cool. So I'm the next speaker, and my name is Xie, and I'm assistant professor at UC Santa Cruz. So today I'm going to give you guys a sanity check on the recently emerged vision transformer compared to like previous CalNet, say which one is more robust. So in terms of the background, in case you're not familiar with the vision transformer, here is a general overview of the working pipeline of vision transformer. Specifically, it provides a completely different way from the CalNets to recognize images. For example, you can see here, first, like it breaks image into different patches, and these patches will go through some linear embedding to project it as some token. And then once we get this token, they add some position embeddings to get the position information and send this to the transformer blocks to process the signal. So compared to the convolutional neural networks, transformer, you can see here, it gets much less inductive bias. And the benefits of this vision transformer is pretty obvious. See, for example, this is a screenshot from the paper with code website. You can see for ImageNet, you can basically all the top 3 models are from vision transformer. And also if you check the COCO detection, again, like the top 3 are vision transformer. And also for this cityscape segmentation, yeah, transformer again. You can see transformer, like even though it just invented like in late 2020, it quickly overtake the dominance of CNN on various standard vision benchmarks. And in this talk, I'm going to give you guys, we check it is a robustness on adversarial examples and on some other distribution tests. So the first work that I'm going to introduce today is a transformer more robust than CNNs. That's our NeuroPeace 21 work. And it's a joint work with Yutong, Jeru, and Alan. So first, let's talk about the setup. Because these are 2 different type of models, right? Convolutional networks, transformers. So in terms of the specific instantiation of these 2 type of models, for CalNet, we choose ResNet, which is the most popular one, right? We choose ResNet 50 specifically. And also for the transformer, we choose data efficient vision transformer. Compared to the default one, this one is the DIT is the first one that can train without using, like say, large scale data set. It just like the exclusive train on ImageNet and with some heavy regularizations, and you can have very good performance. So these are 2 the specific instantiation that we would like to compare it with. And the reason for choosing this 2 type of model is that first, in terms of the number of parameters, they are about the same. For example, ResNet 50, it gets 25 millions. And for DITS, it gets 22 million. And also in terms of the performance on ImageNet, they're also about the same. For ResNet, it's 76.3. For DITS, it's the 76.8. And do note that this is somewhat different from what you're seeing from the DIT paper. The reason is that we following the ResNet training recipe, which will only train whole models for 100 epochs, while the default DIT train for 300 epochs. The main reason that we do this is just because some computation limitation. And also in the paper, we also do a small section, a sanity check on the 300 version, and basically everything that I'm going to state next or holds. Okay, so this is for the fair setup for the scene and transformer. Next, we're going to talk about our evaluation scenario. First, we want to check it is robustness for adversarial examples. More specifically, the adversarial example here is some small perturbation-based adversarial example. That means an image, a clean image, you add some very, very small noise, and you send to the network, and the network screw up. Okay, so that's the situation we're going to consider. And also, to train the transformer and the CNs, we consider adversarial training because this is currently basically one of the most effective way for building robust model. And this is invented by Ian Goodfellow in 2014, and enhanced version was provided by Marjorie from MIT in 2017, I guess. And the basic idea is pretty simple. You get some adversarial images, and then you just send this adversarial images to a network for training. Compared to the standard training, the only difference here is that rather than train with, like, say, clean examples here, you are trained with some adversarial examples. That's the only difference. And it's a very effective, simple to build a robust model. So let's check the results. If we just do the adversarial training to the Robustness 50 and the DITS, and here test we use the PGD 100. Basically, that's a very strong one. And here is the results on the ImageNet. So here you can see that for DITS, it basically got 40.3, while ResNet only got 32.3. That's the gap is around 8%, right? A huge gap. So for this results, we can say maybe in terms of the small adversarial perturbation-based robustness, transformer is much better than the CalNets. But if we take a closer look at the CalNets and the transformer, you will find that first, a very obvious difference is that for CalNets, they use ReLU, and for the vision transformer, they use GILU. Okay, and as shown in one of my previous work, we found that because you can see ReLU here, for the backward pass, it takes an abrupt change at the origin point, right? But for the GILU here, you can see this gradient is pretty smooth. It's a continuous one, right? So in that paper, we show that this abrupt change will significantly weaken your adversarial training. But if you change it to a smooth one, like GILU, you can get much better results. And here is basically the screenshot of that paper. You can see the x-axis is the robustness and y-axis is the accuracy. You can see first, like say, by changing from the ReLU to GILU, the accuracy does not change too much, but the robustness get greatly improved by 9 or 8%. And also, as I just mentioned, a general principle here to reveal the underlying reason that why GILU is better than ReLU is the smoothness also of the activation function. And if you change it to some other smooth active function like the CLU, the ELU, the soft class, you can see all of them are much better than ReLU. So given this prior work called smooth adversarial training, probably we could say maybe the activation function is the key for us to bridge the gap we just observed here, right? So based on this, we additionally do another baseline called ResNet 50 plus GILU, and we can see the result is 40.3, which kind of match the DIT performance. And also, we evaluated these models against some stronger ones called auto attack. Basically, that's a very popular one to automatically evaluating your performance under various different attacks. And you can see under this more restricted more restricted version of attack, you can see auto attack result here. Also, these two are closely matched. And based on these results, we probably will say, okay, under this results, we can conclude that in terms of the perturbation-based robustness, ConvNets and vision transformer, they're about the same. Rather than like a lot of prior work say vision transformer is better than robustness. So we have a different conclusion here. And the key will be the actuation function. And the next thing we're going to check is the out of distribution robustness. Specifically, we consider 3 data sets. The first data set is called ImageSC, which basically benchmarks the robustness against some common corruptions. And also we consider the ImageNet-A data set. Basically, that's our collection of some real-world images, but this real-world images is just pretty hard to recognize. For example, here, you can see the bird here is pretty small, right? Even for human observer, it's a little bit hard than the normal images to recognize. And the third data set is called as stylized ImageNet. Basically, that's just some ImageNet samples go through some stylization. They remove their texture patterns, just keep the shape cues. So on these 3 data sets, we do some evaluation here. And basically, it looks like this. You can see on all these 3 out of distribution benchmarks, you can see DITS significantly improves than the ResNet. For example, on the ImageNet-C, here we use the error rate we follow the original standard in the ImageNet-C, we just use the error rate. So here, the lower, the better. You can see it reduced the error rate further by 4.8. And on the ImageNet-A, you can see the improvement is 5.9. And on the stylized ImageNet, the improvement is 2.2. Okay. And we also do some in-depth sanity check to see whether it could come up from the difference of actuation functions, whether it could be the data augmentation strategy is quite different, because for the DITS, it uses some very strong recognition suite like random aug, mixed up, they use a lot of combination of such things. While for the ResNet, naively, we just train with some like random resize and crop those standard type of augmentations. And also we diagnose the optimizer, because for the DITS, they use add and W for the optimization, where for the ResNet, they typically use the momentum SGD. But after all this diagnosis, we still find that transformer is much more robust than the ConvNets on this out of distribution test. And some further evidence that we conduct here is that we do some knowledge distillation experiments to further align their training discrepancy. For example, here we use vision transformer as a teacher model, and we use the ConvNets as a student model. We want to see by doing this, we can ConvNet take the knowledge from the vision transformer and perform robustly on those out of distribution tests. And here are the results. First, by checking the in-general results, you can see basically the teacher and student, they're about the same, right? So that kind of proves that our distillation here is successful. And then by checking the out of distribution robustness, we find that the ResNet is still much worse than the DITS. So that means by doing some distillation stuff, cannot help ResNet to bridge this out of distribution performance gap. So next, what we do is that we change the role of students and the teacher models. Here, we use ConvNets as a teacher model, and we use the students with the vision transformer. And here are the results. First, again, on the ImageNet, the result looks pretty normal. The DITS and the ResNet, they're about the same. So that means knowledge decision is good. But when you check on the ImageSC, ImageNet-A, and stylized ImageNet, you can see the student models, even like say your teacher model, ResNet, perform badly on this auto distribution test, but student models can kind of say improve this performance about a lot. So this evidence kind of suggests that such stronger robustness comes inherently with the architecture design of vision transformer rather than some other training recipes. So next application we do here is that we try to like say design a hybrid architecture. That means you contain both convolutional blocks and vision transformer blocks. And basically the result is shown in this yellow bar. You can see compared to the red bar, which is ResNet, you get an improvement on ImageNet A, you got an improvement on the stylized ImageNet. But compared to the pure transformer block architecture, like the DITS, you still have some gaps. So these results can further corroborate that our conclusion, let's say the architecture difference is important and have some more transformer blocks can get you better robustness. So takeaways. The first takeaway message is that in terms of adversarial robustness on the small perturbation adversarial examples, transformer and CalNets, they're about the same. We cannot see any obvious difference, say transformer better than CalNet or CalNet more better than the transformer. And the actuation function, the alignment of this from ReLU to ELU or to some other smooth actuation function is the key for getting CalNets perform good on defending against adversarial examples. And the second takeaway message is that in terms of out-of-distribution tests, we perform a lot of ablations, and we can see that transformer is indeed stronger than the CalNets. And through our diagnosis, we can see that transformer blocks is the key for getting this strong robustness. And this is the first work, our newest work. And after we've done this work, we take a deeper rethinking of all the conclusions here. Because here, the only architecture change experiments that we do here is that we get some transformer block, right? But in terms of the vision transformer design, there's also a lot of other components other than the transformer block in this design. For example, we have the patch file operation, right? This is not included in the typical CalNet design. And also we have some position embedding stuff. This is also not used by CalNets because CalNets naively their translation invariant, right? So we don't need to use this information. And also, even in terms of the transformer block, it's already a very compound design, right? Like say, apart from the multi-head attention, which is the core part of our transformer block, we also have we put the norm, like say layer normalization. First, we use a different normalization, layer normalization, right? And also we put the normalization in a different position than the typical CalNet design. And also we still have some other components like the MLP, right? So it seems that we can do some more in-depth study of those CalNets, those vision transfer architectures to further determine which is the key for better robustness. So that's what we're going to explore next. Are these non-transformer specific architecture elements used for robustness? For example, like patch for operation, different position of normalization. This is not specific to vision transformer, right? This recipes can also be applied in the CalNets. So that basically leads to our follow-up work called Can CNNs be more robust than transformers? And this is a joint work with Zeyu, Yutong, and Yu. So first, let's just show you guys the conclusion first. So first, let's recall what we get on the stylized ImageNet and the ImageNet C. We can see that ResNet performs much worse than the DITS, right? And in addition to this two data set, we consider ImageNet-R dataset and ImageNet sketch dataset. So basically, these are another two different datasets to benchmark the model robustness against the same distribution shifts. So first, the trend here is pretty clear that ResNet is worse than the DITS on all these four different data sets, right? And we basically, in this paper, we designed a new ResNet. We call it as robust ResNet. And you can see on all these four benchmarks, our robust ResNet performs much better than the DITS. And here is what we're going to review next for the technical detail of this robust net. Basically, first, like because we're starting the ConvNets, right? So basically, we consider four different types of instantiation of ResNet blocks. The first one is like this. We call it as ResNet depth-wise count. The DW stands for depth-wise count. The reason is that rather than using the typical convolution, here we replace the original convolution with the depth-wise convolution layer. So that's the only difference. And the second architecture is that we change the dimension. For example, original ResNet is a bottleneck, right? First, you get high dimension in the input, you transfer into a lower dimension and then transfer it back to the high dimension. But here we change, we do an inverted version. For example, the inputs only has 96. It first need to upsampling to get our higher dimension, and then on the output it go back to the lower dimension. So that's the main difference compared to the first one. The third blocks basically we move the position of this 3x3 depth-wise convolution layer. We move to the upper one. And also another option is we can move to the to lower position, right? We can move to here. So these are the four different instantiation of convolutional blocks for our experiments. And first, let's recheck on these four different instantiation of convolution blocks, how they perform on this ImageNet data sets. Firstly, you can see that with these four different instantiations, we increase compared to the ResNet, the typical ResNet, we increase the flops, but it's still comparable with the DITS. And then in terms of the ImageNet performance, you can see basically like the DITS is 79.8, and all ours are also pretty close to this number, right? And also in terms of the stylized ImageNet and the ImageNet-C, you can see this networks still performs much worse than the DITS. For example, on stylized, they can get the vision transfer can get 16.2, while ours can at most get 12, right? And for ImageNet-C, it can reduce the error rate to 48.8, 42.8, while ours, the best ones, around the 48, right? And one interesting point is that on the ImageR and the ImageNet sketch data sets, where we can kind of close the gap. It performs these two type of networks by using the depth-wise convolution with higher feature dimensions. They can kind of match the DITS performance. But something interesting that we were going to show next is with those designs, this, like say here, you can see the performance is closely matched with the DITS, right? Next, we will show all those designs. With all those designs that we introduce next, it will perform much, much better than this number. So in terms of our first design that we want to borrow from the vision transformer is the patch fasting. So patch fasting, as shown in this flow work here, is just say, rather than using some convolutional with overlapped regions applied on the image here, we divide images into some non-overlapping regions, and then we use the convolution or or like an inner layer to do the processing. And also by default, in the vision transformer, the patch size, the non-overlap patch size here by default is 16 by 16. Here we also consider 8 by 8 and 4 by 4. We consider all this type of situations. And here's the results. The P4 denotes, like say, the patch size 4 by 4, and P16 denotes the patch size 16 by 16. And first of all, you can see in terms of flops, they are pretty similar to the DETS. Thus introducing this operation, we still keep the network size the same. And in terms of the ImageNet performance, you can see with the small patch size like P4, P8, the performance like nearly doesn't change too much. And with P16, performance change a little bit, like around 1%. But in terms of the robustness, you can see on all these 4 data sets, the stylized ImageNet, ImageNet-C, ImageNet-R, and ImageNet-Sketch, you can see the performance increase a lot. For example, like say on the stylized ImageNet, the original one only get around 10 points, right? Here we can get 17 points. And also like on the ImageNet-C data set, we can reduce the error rate by around 6% with the P16 here. And on the ImageNet-R, the improvement is around 3%, and the Sketch data set is around 3% again. And also you can see the improvement, like such trend is monotonic. You can see with large patch size employed here, you keep getting better robustness. And this is for our ResNet depth-wise block instantiation. We also have the results on other block instantiation. And basically the results, the conclusion I just told you guys stay holds. And this is first one, the patch file operation, and we find it's pretty useful. The next operation that we want to do is we want to get larger kernel size. So as popularized by VGG network, modern CNNs prefer to use like the small size convolution kernels like 3 by 3. But for the vision transformer, because you use the self-attention, right? Then like you can kind of modeling the low range interaction between different inputs. So motivated by this, we then try to say, okay, I want to use maybe 5x5 convolution layers, kernels, and maybe 7 by 7, and maybe even larger, like 15 by 15. And here is the results. Again, you can see with larger kernel size, you always get better, like say, better results on the ImageNet, better results on the stylized ImageNet, ImageNet-C, ImageNet-Sketch, and ImageNet-R. Though like the trend is not as monotonic as the patch operation we just seen, but you can see overall, it improves the robustness very substantially by using large kernels. So that's our second point. We want to say for ConvNets, you should use large kernels. And the third thing that we are going to do is we want to reduce the activation and normalization layers. So by default, you can see that for this 4 different instantiation here, we always append our batch normalization and a ReLU after the convolution block, right? And if you have read the recent ConvNets paper, this shows that if you just say in the whole block, you just use 1 layer normalization and 1 DLU, and the performance can even improve a little bit, though not very substantial, but it still improves the performance a little bit. And another benefit by using less normalization and activation here is that you can reduce the memory in the training and also improve the training speed. So inspired by this ConvNets design to say use less convolution layers, less normalization layers, we also do some search on these 4 blocks. And basically we find the optimal design basically look like this. And all these 4 has quite different designs. For example, for the ResNet depth-wise, the first one, you should append a being after the first one and add the ReLU after the addition here. And for the ResNet invert one here, you should add a being ReLU right after the first 1 by 1, or for other positions, you just do not add anything here. And for the third one, you can see like first, for the first block, you add a being, and for the second block, you add a ReLU. And for the last instantiation here, you should add a being ReLU right after the first one. So that's our optimal design. And basically, the result is shown here. With such design, first, it does not affect the flops. It even improves your training speed, reduce the memory in training. And in terms of the ImJet performance, you can see they perform pretty close. On the ResNet is like a slight decrease performance by 0.3, but for others, you can see improved performance by ranging from 0.4 to even 1.9%. And then we check on the stylized ImJC, ImJR, and ImJS sketch data set. You can see all this data set get some very substantial improvements. For example, like if you look at the ImJC data set, the error rate can reduce by 2.9 here. And also you can see, like say, for the sketch data set, the improvements is around 4%. So basically, all the components we find, and we just find and further evidence that by like say combining this patch fasting, large convolutional kernel size, and less actuation and normalization together, you have the robust ResNet architecture, and it can perform even more robust than the DIT the vision transform architecture. And this the experiment is done on the ResNet 50 scale, and we also do some scaling up. We try to do the DIT base model, and we find that the conclusion still holds. With our robust designs here, you can see it can perform, though like on the ImJet performance, it's kind of match here, but you can see on the robustness test, some models can perform much more robust than the original DIT-based model. So takeaways, based on this paper, we find that in terms of out-of-distribution robustness, we still can not see an obvious, like say, performance gap between the vision transformer and the CalNets. And CalNets, even with the designs that we introduced here, they can be much more robust than the vision transformer. So architecture elements again matters a lot in this out-of-distribution test. So lastly, I want to thank to my collaborators and also the OpenFail and the Google research for providing some credits for running the experiments. And lastly, I want to do a small advertisements for my lab. We still have some intern positions for remote visiting students. And if you're interested in the works that I just talked about, or the robustness in general, or some self-supervised learning stuff, you are welcome to send me an email, and I'm happy to discuss. And that's all. Thanks. And I'm happy to take questions if there is any.
Hello, can you hear me?
Yeah, I can hear you. Yes.
Great talk. I have one question. Could you please give us a very intuitive explanation about why the HashiCorp design is such important for the robustness?
Which component?
Hash mining.
The patchify operation, is that right? Sorry, I hear a lot of noise there. I'm not sure if I understand your question correctly. So you're asking for why patchifying is important, right?
Yes, I mean, why is so important?
Okay. So for this part, yeah. To be honest, I do not have a very clear, like, to explain what underlying like this works. We just empirically first showing that this is something pretty important by stabilizing this network to get much better robustness. And even in one of our recent work, we found that this patchifying operation is good even for adversarial robustness training. So we're still trying to understand the underlying reason, but it turns that besides this out-of-distribution robustness, maybe for some more general robustness tasks, this patchifying is pretty important. But we're still trying to understand this.
And so, and also, could you try this design of patchifying on recently proposed convertex? We also see the signal of the patchify and can bring the improvement of robustness of the convertex.
You mean include the patchify for what? Sorry, again, sorry.
Convertex.
How? What? Sorry.
For the convertex, can
you? You're referring to the patchify operation for the general CalNet. Is that what you're talking about?
No, I mean, recently, the researchers proposed a new convertex and its main CalNet.
The CalNet paper, right?
Yes.
Oh, yeah. So yeah, I think CalNet paper, yeah, again, like it used a patchify operation, right? But in the CalNet paper, it shows that patchify operation does not, if I remember correctly, it does not mean you will improve the standard accuracy. It just shows that by bringing this patchifying design, the CalNet architecture can still perform very good on the standard vision benchmarks, right? So I think that paper first show patchify is a legitimate operation that we can safely introduce into CalNet. And why we're here is that we discover it is additional benefits to say, okay, first you guys show that it's durable with CalNet, is not affecting your performance too much. But here we show that in terms of robustness, patchify operation is great. Here we show on the auto-distribution robustness, and there are some our other works we show in terms of the adversarial robustness, it also helps. So I believe that that's a very specific in terms of this patch operation. It's a very good one to get a full starting. I hope I answered your question. Okay. Okay, cool. If no more questions, let me.
So you basically looked at when you increase the kernel size, you get better results. But I was wondering, did you compensate for the additional parameters that you have?
Oh yes. So let me first repeat this in case I understand it wrong. So because I use large kernels, right, then I will have more parameters. Do I compensate this parameter increase to do a fair evaluation, right? Okay, so yes, so what we do here is that once we do some increasements, if I remember correctly, we try to reduce the ConvNet blocks to maintain the computation nearly stay the same. I think compared to the traditional ResNet, like say changing from 3 by 3 to 5 by 5 or even to 7 by 7, the computation increase is not that much. It's because we're using depth-wise convolution rather than using the typical convolution. So in using the depth-wise convolution, the increase is not like a huge amount. It's still a reasonable amount. And I believe we still do some parameter control to make sure the comparison here stays fair. Okay.
Thank you.
Mm-hmm. Okay. I got another question from the chat. Maybe let me first read the question. In the design of less activation and normalization layers, there are many choices in the number and location of activation and normalization layers in different ResNet blocks. You only use one activation and one normalization. What criteria you use to decide the number and the location of activation and normalization layer? That's a very good question. So what we basically do here is that we do some just some naive search, some combinations. For example, we try to first I think the first thing that we do is we keep the batch normalization untouched, and then we try to remove ReLU and see what is the results. And once we determine the optimal location of ReLU, because here we just need to do 3, right? There are 3 locations, like one, like say, one could be here, and one could be here, and another could be here, right? So we try different 3 ReLU locations, and we do all such experiments. So we find which one like stays the best for the ReLU. And then we fix this ReLU location. Then we try to take out the batch normalization layer, and then see which one gives us the best results. So it's try and error. There's no like golden rules to guide us to select the best position. But yeah, just through some try and error, and we identify these positions. Okay.
Question like what what should I do? Do like focus on practical tax? I'm really
Can you closer to the computer? I cannot hear the question very clear. Sorry.
There seems no more questions.
Oh, okay. Okay, cool. So I guess I will play the video for the Louis next, right?
Yeah, you can quickly introduce him and then. Okay.
You have the video, or I should play the video?
Yeah, I do have the video. You just
Okay.
introduce.
Cool. Okay. So our last speaker is Louis. Louis is an assistant professor in computer science at University of Washington. His research interests revolve around the foundation of machine learning, often with a focus on dataset evaluation and reliable methods. His topic is limits and opportunities of adversarial robustness. So yeah, you guys can try to play the video here. If you find trouble on playing the video, I can also play on my end.
So we are working on that. Should be okay.
Cool.
Hello, everyone. I'm Ludwig Schmidt. I'm an assistant professor in computer science at the University of Washington, and I'm really excited to be at this workshop today. Thanks a lot to the organizers for the invitation. I would have loved to attend in person. Unfortunately, there were some changes to my travel schedule recently, so I can only be at CVPR starting tomorrow. I'm very much looking forward to meeting many of you in person over the coming week. But for now, we'll do this talk as a recording. So thanks to the organizers, especially for being flexible with the format of this talk. Good. So let's get started. Adversarial robustness. This has been a really exciting field to be in and to follow over the past 5 years. As a community, we've learned a lot about how to make neural networks more robust to adversarial attacks. And we've learned a lot about how to probe neural networks for various vulnerabilities. I think this will be broadly useful across machine learning in the coming years. Many cool insights have come out of this research direction. But for today, I want to do something a little bit different and not talk actually about research advances in core adversarial machine learning, but something a little bit more around it. And I think this goes nicely with the theme of today's workshop. Let's just remind ourselves, so the theme is different from the previous workshops on adversarial machine learning. Our proposed workshop aims to explore both the devil and angel characters for building trustworthy deep learning models. So I thought, okay, this is a nice theme. I'll structure this talk also in 2 parts, following the devil and the angel characters. So the overall question for this talk is, when is an adversarial robustness perspective useful? And in the first part of the talk, I'll take the perspective of the devil's advocate. Specifically, I'm going to ask, does adversarial robustness actually promote reliable generalization in real data? And what we'll see is that while adversarial robustness does help against true adversaries, if you go to more benign settings and look at distribution shifts arising in real data, then they are only limited to no gains from adversarial robustness in promoting that at training time. But overall, I think this is one facet here, sort of like the devil side. In the second part of the talk, I switch to the angel side because I'm still very excited about adversarial machine learning and ask the questions, what applications follow a truly adversarial model? And we'll see that the US criminal justice system has many opportunities for doing research with an adversarial perspective on machine learning. Good, so let's get started with the first part. Does adversarial robustness promote reliable generalization? So if we make our models more robust from an adversarial perspective, do they become more trustworthy overall? And in order to answer this question, we'll look at a paper that I wrote towards the end of my postdoc at UC Berkeley. This is with a set of really great collaborators from UC Berkeley, and then also friends from CMU and Google. And at the time, so this was about 2 years ago, the question that we were interested in was, okay, there are now so many different notions of robustness that people studying in the robustness community. How do all of these different types of robustness relate to each other? And one of them is obviously adversarial examples. Everyone here is familiar with that, but we also know that there have been many different types of robustness in the literature. For instance, one of them is video perturbations. You can look at the small changes in images that occur in adjacent frames of the video, and then see if these small changes also confuse image classifiers. Another very widely studied type of robustness are image corruptions, like adding Gaussian noise or adding a synthetic rain pattern or a motion blur pattern. Yet another type of robustness is dataset shift. We look at this in a bit more detail soon, where people have collected new test sets, for instance, new test sets for ImageNet with a distribution shift to specifically check for this type of distribution shift that arises in real data. And then another one that people have studied a lot is various geometric transformation. Like if you have a rendering setup, for instance, you can easily change the geometry and see how robust your classifiers are to these kinds of perturbations. Good, and all of these are interesting research directions. And a priori, an important question is, how do these different types of robustness fit together? When we make progress on one of these robustness notions, are we also making progress on other types of robustness notions? Are we building models that are broadly more robust, or are these different kinds of robustness more disjoint? Because overall, the goal obviously is that we would like truly robust models that can do all of these things because humans are robust in all of these different ways. Okay, in order to answer these questions, our approach was basically just to evaluate everything that was out there, both on the side of models and on the side of distribution shifts. So we focused specifically on ImageNet because people had proposed many different models, robustness interventions, and many different distribution shifts for ImageNet. And so what you see here, sort of like as the core experimental object of study in this paper, is a big evaluation grid. So every row here corresponds to one model in our testbed, and every column corresponds to one distribution shift, one test setting that we are evaluating the models in. So every small cell here in this matrix corresponds to evaluating one model on one distribution shift, and then we record the corresponding accuracy. And just to give you a bit of a better sense of what's actually in this grid, what's in our testbed, let's first look at the y-axis here, the 200 models. At a high level, you can think of them as divided into 3 different types of models. One is what we call standard models. So these are models that are just trained with a focus on ImageNet accuracies. The goal in these papers was just getting higher and higher ImageNet accuracy. So they serve as a very good baseline. The second type of model that we look at in our evaluation are various kinds of robustness interventions like adversarial training, randomized smoothing, specialized types of data augmentation, special filtering layers, and so on. And then the third type of model that we'll highlight are models trained on more data. So all of the other models are only trained on ImageNet, and some groups also pre-trained their models on much larger data sets. And it's interesting to see what the robustness impact of that is. Okay, so this was the model dimension. And then on the other axis, the distribution shift dimension, again, we just tried to get everything that's out there into our testbed. So we have a variety of different test sets that were collected in the ImageNet context, like ImageNet v2, ObjectNet, ImageNet R, ImageNet Sketch, ImageNet A, ImageNet with Robust. Then we have a range of different adversarial evaluations with different LP norms of different strengths. We have all the image corruptions in there and so on. We're also happy to expand this. If you have certain suggestions for things we should include, please let us know. For now, we'll go with this grid. And the focus today is going to be specifically on what we call natural distribution shifts in this paper. So what do we mean by this? We mean test sets that are related to the standard in distribution ImageNet test set, but different in an important way. So the test set contains only real images as they were recorded, no adversarial perturbations, no synthetic image corruptions, only real images, but collected with a different data collection process. And I think this is a very interesting test case for robustness, because in the end, we wanted our models are more robust on real data. And these distribution shifts are examples of real data. So sometimes with synthetic perturbations, it's unclear how well it transfers to real data. If we look at these natural distribution shifts, we know at least it's real data. And the 4 examples we're going to look at in more detail in this talk are ImageNet v2, ObjectNet, ImageNet Sketch, and ImageNet R. There's obviously a lot more work in the robustness community on cool natural distribution shifts that test models in a variety of ways. Just 2 examples here are wilds and breeds. They're also very nice. For here, we focus on these 4 test sets because they are directly compatible with models that are just trained on the standard ImageNet tasks. So for wilds and breeds, for instance, you need to train models specifically on these test sets, and we wanted to use this large set of pre-trained models for ImageNet that's out there. Okay, and then the big question is, do current robustness interventions yield robustness on these natural distribution shifts, on these 4 examples? And now, if we talk about, okay, what does it mean for a model to be more robust on these natural distribution shifts? We need to look at them in a little bit more detail. So, and we will do this as follows. This is going to be one of the key plots in this talk. On the x-axis, we'll have ImageNet, just a standard test set, top 1 accuracy. On the y-axis, we'll have accuracy on the test set with distribution shifts. So to make this concrete here, we'll use ImageNet v2. And now every point, every dot in this plot is one model in our testbed. For now, I've started out with the blue points here being what we called earlier the standard models. So these are models just trained on ImageNet to do well on ImageNet. And we had everything in there at the time, from the seminal AlexNet paper over standard architectures like VGG, ResNet, DenseNet, Inception, and so on, to the state of the art at the time among models just trained on ImageNet, EfficientNet v7. And one thing that stands out when you look at this plot is that all of these standard models are on a quite clean linear trend. So I've added a linear fit here, the red line. And this is interesting why that happens in the first place. We'll not talk about this today, but for now we'll just take this as a given, because this linear trend is going to be a very good baseline for understanding how robust models are. Because if you give me a new model and you tell me it's ImageNet accuracy, just by looking at this linear trend, I can tell you what I would expect as out of distribution accuracy. So for given in distribution accuracy, I can give you as a baseline, okay, I would expect that this model has a certain out of distribution accuracy just because it's probably going, or as a baseline, it would behave like models trained on ImageNet, like these blue points, the baseline models, the standard models. And then what we would like to do, or what ideally what a more robust model should achieve, it should be above the red line, right? So the red line is what we get just from standard ImageNet training. If a model claims to be truly more robust, we would like to be closer to the y equals x line. So y equals x here is same performance on both in distribution and out of distribution. And we know that for this specific distribution shift here, ImageNet v2, this is a reasonable goals because humans can do this. We actually did this experiment with 5 expert labelers. They get the same accuracy on ImageNet and ImageNet v2. So if we want to have our models to be as robust as humans, then they should achieve what we call effective robustness, basically be above the baseline given by the standard ImageNet trained models. Okay, and then the big question is, okay, for all the models in our testbed, do any of them achieve effective robustness? Like, can they go above this baseline given by the standard ImageNet trained models? And in order to answer this question, let's take this plot and let's just add all the other models in our testbed. So we plot all of the 200 models. And then you get the following plot here. And at first sight, this may look like just a plot before. There are more points here, but there's actually not that much going on. So basically, we added 2 more classes of models. Brown points are the robustness interventions like adversarial training and so on. And the green points are the models trained on more data. And the first thing you see is nothing really stands out by a lot. So none of the models in our testbed achieve a lot of effective robustness on ImageNet v2. And specifically, most of the brown points are actually on or very close to the red line. If you look in the higher accuracy regime on the top right, there are a couple of data points, a couple of models that stand out, a couple of green points. At the top right is a model trained by researchers at Google on 300 million images. So a lot more images than the 1 million in the ImageNet training set. There's another set of models pre-trained on a lot more data. These models were trained at Facebook on 1 billion images from Instagram. And then there's one more green point that stands out. And this one was trained on the full 21,000 class ImageNet. So about 20 times more training data than ImageNet. So it seems like more data does offer you a small amount of effective robustness, but overall the gains are limited here. And this is not just ImageNet v2. Another data set that we looked at in our study is ObjectNet. So this was built by a team of researchers at MIT. And they set out with a data collection process based on Mechanical Turk to collect specifically challenging images for the object categories in ImageNet. This is a very nice experiment. And then we took their test set, fed it in our testbed, and we got the following plot. So you can see there's still a quite clean linear trend mapping in distribution to out of distribution accuracy. It's a little bit more noisy now. And the only models that stand out above the red line are again the green points, so the models trained on more data. So adversarial training and other robustness interventions again give you only limited or no gains on this distribution shift. Good, so let's go to the next 2 examples we had of natural distribution shifts. And those were ImageNet Sketch and ImageNet R. So again, real data. People collected these images off the internet. ImageNet Sketch, obviously, as the name suggests, they are all sketches. ImageNet R you can think of as a supercharged version of ImageNet Sketch that contains a variety of renditions, not just sketches, but also paintings or various sculptures and so on. Anything but actual images of the real object. And okay, let's look what the trend is there. So here, overall, we still have if you only look at the blue points, a pretty decent linear trend. Again, it's a little bit more noisy. At the top right, the best models with a pretty good margin, again, are the models trained on more data, so the green points. One interesting thing is that some of the brown points now stand out. So these are models with specific types of data augmentation. And another set of models that stands out here are the yellow points here. So what I did on this plot here is specifically highlight the models trained with adversarial robustness in mind. And there's one set of models. This is a paper, again, from Facebook. The paper where they did adversarial training at ImageNet scale for the first time and combined it with some denoising layers. And for some reason, these models have a lot of effective robustness for ImageNet Sketch. I don't actually know what the reason for this is. I think it's an interesting research direction. But one thing to keep in mind is that here adversarial training does achieve high effective robustness, but these models are, if you just train them the same architecture in a standard way, they already achieve comparable out of distribution accuracy. So what's going on is more that you're making a model worse in distribution while maintaining its out of distribution accuracy. So it's unclear if you sort of like should do adversarial training here to actually make the model better out of distribution. And overall, the best models are still the models trained on more data. But I think understanding what's going on here would be very interesting because you see a similar trend on ImageNet R. So ImageNet Sketch is on the left, what we've just seen. On the right here, ImageNet R, and overall the two test sets generally have similar behavior. So the best models at the top right are the models trained on more data, and then some of the adversarially trained models stand out, but overall in a much lower accuracy regime. Okay, good. So this is overall the state of these 4 natural distribution shifts. And when we did these experiments in 2020, we thought this was overall a pretty sobering result because out of the, say, ImageNet V2, 12% accuracy drop, out of that 12% accuracy drop, even training on 1,000 times more data, like the Instagram models here, only give you about 2 percentage points. If you do a naive extrapolation of that to fully close the 10 to 12% accuracy drop, you would need about 10 to the 10 to 10 to the 15 times more data. And it's obviously unrealistic. So this looked like we really needed new ideas in order to make progress on these natural distribution shifts. But then in early 2021, the CLIP paper came out from OpenAI. And this was super, super exciting from a robustness perspective. I'm sure many of you have seen this CLIP paper before. Basically, OpenAI demonstrated that you can train multimodal image text models on a large weakly supervised collection of images from the internet. These models have many interesting properties. One of them are that they are way more robust to distribution shift than anything we had seen before. So this is straight from their blog post where they announced the model. And what they did there was exactly what we suggested people should do, this effective robustness evaluation. So they compare the accuracy of a CLIP VITL model here to ImageNet trained ResNet 101 as a baseline. So they match the ImageNet accuracy. Both of them have 76.2% on ImageNet, and then they compare the out of distribution accuracy. So basically the numbers we are looking at are exactly how far above the ImageNet trained baseline are you in these scatter plots. And then the effective robustness numbers that CLIP achieved are just really, really large, like plus 6% on ImageNet V2, plus 50% on ImageNet R, plus 40% on ObjectNet, 35% on ImageNet Sketch, and plus 74% on ImageNet A. And if you follow these large image classification data sets that are very competitive like ImageNet, you know that large double-digit improvements are very, very rare. This basically can't happen too often because if you get plus 50% twice, you're done with the benchmark, right? So this was really, really exciting. And then when you look more at the paper, they also do these scatter plot evaluations. And basically here what we should look at is the orange line. These are the CLIP models evaluated in a zero-shot way, and they're just much better than any of the other models that are in our test bed. So they used our test bed in order to evaluate the CLIP models. So this was really, really interesting to see, but obviously also many research questions came out of that. So one obvious one was, why is CLIP so robust? Is the language part crucial for making the models more robust? Is it the images in the pre-training set? We really didn't know. And the other one is that while we had these really large robustness gains with the zero-shot models, once you start fine-tuning the CLIP models, actually a lot of the robustness goes away. So the red line here is basically the fine-tuned version of the orange line. So this is what you get when you fine-tune the CLIP models. And then they're still better than previous models, but not that much better anymore. So there was a question, can we combine the improved in-distribution accuracy you get from fine-tuning with the really good robustness, out-of-distribution robustness that the CLIP models offered? And I'd love to tell you more about this, but this is maybe more the topic of a different talk. Over the past 1.5 years, my research group has done a lot of research around CLIP, understanding why it's so robust and how to leverage CLIP in an effective way on downstream tasks. I'll just quickly tell you some of the key points here. One is that it is actually quite easy to overcome this trade-off between robustness and fine-tuning. If you do what we call weight space interpolation for fine-tuning, then you can get both good robustness and the improved performance on your target task. And then if you combine this with a couple more ideas and use the largest image text models from Google, then you can actually get image in state-of-the-art accuracy via these improved fine-tuning ideas. The other question was, where does CLIP's robustness come from? At a high level, I think the key question was, is it the language supervision or is it the more diverse image part of their data set? And the answer to this is actually surprisingly clean. Language supervision plays effectively no role in improving robustness here. The only point of the language supervision is that you can train on a more diverse set of images. So all of the robustness really comes out of the image part. You can make this more precise. You have the experiments in the paper. You should have a look at the reference there if you're interested. And the other direction, if all of the robustness comes off the pre-training data set, then obviously the question is, how can we design better pre-training data sets? I think it's a very interesting research direction. We'll have a paper on arXiv on that in a couple of days. But for now, I'll just leave you with a link to the OpenClip reproduction for CLIP training. So we also built this GitHub repository where we are training larger and larger CLIP models together with the friends at the Lion project to build the big Lion data set. So the point here is just this CLIP direction is really interesting from a robustness perspective. And we are also getting to a point where people in academia outside the big corporate labs can do really interesting experiments with CLIP. Okay, let's go back to the overarching question for this part of the talk. Does adversarial robustness promote reliable generalization? Are we getting broadly more trustworthy models? And the answer is, it's so-so. Like clearly adversarial training does something. Like if we train models with adversarial training or randomized smoothing and so on, the models do get better against adversarial attacks, and that's great. This is what the methods are primarily introduced for. But if we want broadly more robust models, then an important question is also to ask, is this adversarial robustness transferring to other types of robustness? And there the answer seems to be no. In some of the data sets, there's a bit of transfer, but overall, currently, the transfer is limited. And other approaches that, like what we've seen OpenAI's CLIP model, seem to be a bit more promising for enhancing robustness on natural world distribution shifts. So as I said, I think pre-training, improving the pre-training process, creating more diverse pre-training data sets is a really interesting research direction there. And then if we say, okay, natural distribution shifts, maybe adversarial robustness isn't the thing to do there, then the question is like, in what applications do we have a truly adversarial threat model? And this is now, as we said, the second part of the talk, where we take now the angel role and highlight a really interesting research opportunity where an adversarial perspective is really useful. Okay. And the application we are going to look at is the US criminal justice system. This is again a collaboration with many great people at UC Berkeley, in Tübingen, and UW myself. And in Berkeley, we collaborated both with people in computer science and with people in law. This is a really interdisciplinary collaboration. And just to give you some background, let's start with the US criminal justice system. So how does this work? Because there are actually quite important differences here, for instance, with European criminal justice systems. So at a high level, there are 3 parties that are involved in a court trial in the US criminal justice system. There's the judge and the jury, and their role is to overall sort of like moderate the process and at the end reach a decision. And in order to reach a decision, they should rely on evidence, and this evidence is going to be provided and questioned by the prosecution and the defense. So the prosecution's goal in this overall process is prove the defendant is guilty. So this is important. It's not an unbiased prosecution that is going to do an unbiased fact finding. Their overarching goal is to show that the defendant is guilty. And in order to make sure that they can't just come up with wrong evidence, on the other hand, we have the defense, and their goal is to disprove the prosecution's case, basically undermine what they are saying in order to show that the defendant is not guilty. And so we have basically an adversarial process here because the prosecution and defense are directly pitted against each other. And the idea is that the system as a whole arrives at truth via this adversarial process. And probably the way I phrased this, you already can see some of the connections to adversarial machine learning. You can think of the role of the defense here as that of a white hat hacker. So like basically the defense wants to break or attack the evidence produced by the prosecution. Okay, so this is classical law. There's nothing new here. This is just a background. How does this connect to machine learning, and where does adversarial machine learning come in? And one key point here is that the courts increasingly rely on software-generated evidence. So one illustrative example here is the trial of Maya Herskovich. So just for background, let me explain this a little bit. So in 2013, Maya Herskovich, who is a Hasidic man living in Williamsburg, New York, was convicted of a violent assault and sentenced to 4 years in prison. And an interesting aspect here is based on what evidence did they reach this decision, because the victim in this case did not actually identify Herskovich in court. Moreover, Herskovich has no criminal record and he was not seen on any of the surveillance video for this case. So why were they convinced enough that they should convict Herskovich in this case? And a key piece of evidence, the key piece of evidence in this case really was a DNA sample, specifically just under 100 picograms of DNA that the prosecution obtained from the victim's sneaker. And it contained at least 2 persons' DNA. So just for context, 1 picogram is 10 to the minus 12 grams. And then the prosecution analyzed this DNA sample with an in-house developed software and claimed that it was 133 times more likely than not that the DNA sample belonged to Herskovich. And there's a big caveat with this, is that the defense lawyers could actually not scrutinize the software that was used against Herskovich in this case. And when you look at this from a perspective of a computer scientist, or specifically from a machine learning researcher, a lot of alarm bells go, obviously, right? We know that software can have many bugs, and especially for statistical software, machine learning tools, we often really don't understand the failure cases yet, right? This is why adversarial examples attracted so much attention, because the network set is really counterintuitive failure cases. So a priori, it's really unclear how reliable are these DNA tools here. And this is exactly also a point that the defense then made. So the appeals lawyer, Donna Aldea, said, this case is a poster child for how DNA evidence can literally be fabricated out of thin air, and how statistics can be manipulated to create a false impression of scientific evidence of guilt. And a bit more in detail, nuanced, the lawyer's argument was that the software that the prosecution used may well work in some cases, but it has not been validated on this population of interest here. Specifically, as we said, Herskovich is part of a community of a specific ethnic group, the Hasidic Jews of Williamsburg, and they likely share many of the same ancestors and therefore much of the same DNA. So some of the validation studies that the prosecution may have done on different populations, it's really unclear if the if the outcome of these validation studies has any bearing here for the validity of the evidence in the specific case. And this is just one illustrative example here. Software generating evidence is now quite commonly used in the court. So ProPublica has done a lot of good work highlighting how widespread this now is. For instance, in one article, they pointed out that thousands of criminal cases in New York relied on disputed DNA testing techniques. And according to the vendors of these DNA testing software, it has been used already in more than 200,000 cases. And again, this is just one kind of evidence here and one set of tools. So software generated evidence appears now in a variety of ways. Our classical way of bringing sort of like scientific evidence into court trials is breath testing. People have probably heard of that, but there are also newer examples, like for instance, environmental audio detection. ShotSpotter is one example. The idea is that these tools classify environment sound as gunshots in order to alert the police, and sometimes this is also used as evidence in court trials. Another one is tool mark analysis, where people use computer vision techniques to analyze the surface of bullets and match it to a specific gun. And again, there are more tools out there. This is for us also currently a process of figuring out where are software tools used to generate evidence. And basically our proposal here is that we should really connect these two notions of adversarialism in the law and on the machine learning side. As we said, this US criminal justice system is explicitly set up as an adversarial process. In terms of motivating why we should take an adversarial perspective, it doesn't get more clear than that. Like, this is really a key piece of the system in order to ensure that the overall system arrives at the right outcome. And of course, on the machine learning side and adversarial machine learning, we have developed a lot of insights for how to test the reliability of machine learning models, how to make the models more robust, the role of distribution shifts, and so on. So I think there are many interesting technical questions here. Like, first of all, what tools to study? What are their failure cases? What are interesting distribution shifts, the perturbation models, and so on. So this is very much ongoing work. I would be happy to chat more with people about this. But in the interest of time, since we are at exactly 30 minutes now, let's conclude. Good. So if you take a step back, the past 2 years of robustness research, lots of exciting advances, and people have studied various types of robustness. And I think what we are learning now is that these different types of robustness can sometimes be quite orthogonal. So making progress on one type of robustness does not mean that your model gets broadly more robust and also solves other robustness challenges. So I think one research direction here is just mapping out what these different kinds of robustness are. One concrete thing we can currently already say is that adversarial robustness does currently not seem to help much with natural distribution shifts. So if you're outside a truly adversarial evaluation, maybe other techniques are more suited. For instance, what we've seen that OpenAI's CLIP model made a lot of progress on these natural distribution shifts. On the other hand, there are very much applications that call for an explicit adversarial setup. Security is one motivation that we often have talked about in adversarial machine learning, but I think there are actually many other interesting applications as well. And one where I think we have a lot of opportunities and work to do is at this intersection of adversarial robustness and the US criminal justice system. So thanks a lot for listening. If you have any questions, please find me in the coming week at CVPR or just send me an email. I'm also happy to talk more via email. Thanks.
Okay, thank you all for coming. And today is that's all of the content of the workshop. Thanks again for coming.
Hi, Yingwei.
Hi.
Will you able to terminate this Zoom, or we just keep it?
Yeah, I'm the host. I can do that.
Okay, cool. Then just let's terminate this one.
Okay, thank you.
See you.